Now that we got through some administrative stuff, we're going to immediately dive into our first technical topic. In this section, we're going to start to look at some of the internals of Node.js. Once we have a better idea of how Node works internally, we'll then be able to leverage that knowledge to write some more performant code inside of our applications. So let's get started right now. We're going to start off by taking a look at a very simple diagram. And then over time, we're going to come back to this diagram right here and add on a lot more detail to it to show you how Node is internally structured. So here's our first iteration. At the very top, we've got a box that represents the JavaScript code that you and I write. So this is the actual code that we place into JavaScript files and then eventually execute at the command line. When we run node and then index.js at the command line, we are invoking the node.js project. Now, just like any other JavaScript project out there, Node.js internally has a collection of dependencies that it uses to actually execute your code. Two of the most important dependencies, and these are two dependencies that we're going to focus on quite a bit throughout this course, are the V8 project and the Libuv project. The V8 project is an open source JavaScript engine created by Google. The purpose of this project is to be able to execute JavaScript code outside of the browser. And that's what we do when we run our JavaScript code from the terminal. The Libuv project over here is a C++ open source project that gives Node access to the operating system's underlying file system. It gives us access to networking, and it also handles some aspects of concurrency as well. So anytime that you show this diagram to someone, their first question might be, okay, so we got one module right here that gives us access to the file system and networking and other stuff. And then we've got this one right here that actually executes our JavaScript code. So what is the purpose of Node.js? And that's a very good question. So I want to give you an idea of why we use Node at all and why we don't directly use V8 or Libuv. The first thing to understand is that internally, some of these other libraries are not JavaScript code at all. The V8 project is like 70% C++ code, and Libuv over here is 100% C++. So chances are that you, as a JavaScript developer, you probably don't want to be writing C++ code all day. You want to write JavaScript code and just have it work. So that's one of the purposes of Node.js. Node gives us a nice interface to use to relate our JavaScript side of our application to the actual C++ that's running on our computer to actually interpret and execute our JavaScript code. The other thing that Node does is provide a series of wrappers and a very unified and consistent API for us to use inside of our projects. So for example, Node implements the HTTP module and FS, Path, Crypto. All these modules right here have very consistent APIs, and they all ultimately refer to a functionality that is mostly implemented inside of the Libuv project over here. So again, you probably don't want to get access to direct C++ code. You want to require in some JavaScript function and use a JavaScript function inside of your code base. So by making use of Node, you don't have to work with all the C++ that exists inside of Libuv itself. Okay, now we've got a better idea of why we use Node at all. Let's take a quick pause right here, and we're going to continue the next section and continue fleshing out this diagram. In the last section, we started talking about the internals of Node.js, and we had said that the purpose of Node is to give us a nice, consistent API for getting access to functionality that is ultimately implemented inside of V8 and Libuv. I want to give you a very concrete and practical example of how this actually works behind the scenes. So in this section, we're going to go through a little bit of an exercise. This is going to be a lot of fun, but it is going to revolve around kind of clicking around to a lot of different pages inside of our browser. So we're going to look at some different documentation and some source code, but along the way, you'll get a much better idea of what Node.js is really doing for you and me. So this exercise that we're going to go through is this right here. Here's what we're going to do. So at the very top, we're going to first start off by picking out some random function inside the Node standard library. We're then going to try to find where that function is implemented in the Node.js source code. So like the actual source code that comprises the Node project. And then once we find that source code, we're going to figure out how Node leverages and kind of wraps functionality that is implemented inside of libv8 and libuv. So this is going to be a really fun exercise, and it's going to give you a much better idea of how Node is internally structured and how it works. So step one is to pick a function in the Node standard library. Now, I had said that we were going to pick a random one, but in truth, I already picked one particular function out, and this is going to be a function that we're actually going to use quite a bit later on inside the course as well. So the function that you and I are going to investigate is called, well, let's pull up an example of it right here. Here we go. It's going to be a function called pbkdf2. So that's the actual function name right there. And I know that's a really weird function name. It's the name of an algorithm that is used for hashing some arbitrary data. So this is a function inside of Node's crypto library. And usually it is used to hash a password for storage inside of a database. So again, I know it's a weirdly named function, but it's just the name of some hashing algorithm. That's all. So let's take a look at the actual implementation of pbkdf2 inside the Node codebase. And as we go through this process, you're going to very quickly see how Node internally makes use of libuv and the v8 project as well. All right, so I'm going to pull up the nodejs source code on github.com. If you want to follow along, you can open up your own browser and go to github.com nodejs/node. All right, here we go. So here's the Node repository. This is all the source code that you have already installed on your computer when you installed Node. Inside this repository, you're going to find a bunch of different files and folders, but there's two folders that are very relevant for what we're trying to do right now. There's the lib directory right here and the src directory right here. The lib folder contains all the JavaScript definitions of functions and modules that you and I require into our projects. So you can think of this lib folder right here as being like JavaScript world, or the JavaScript side of the Node project. Then inside the src directory is the C++ implementation of all those functions. So the src directory right here is where Node actually pulls in libuv and the v8 project and actually fleshes out the implementation of all the modules that you and I are used to using, like the FS module, the HTTP module, and so on. So let's first get started by looking up that pbkdf2 function inside this lib folder, and we're going to find the JavaScript definition of that function. So inside of lib, we're then going to find the internal directory, which is right here. We'll then find the crypto directory right here. And then finally, we'll find the pbkdf2.js file. Here it is right here. All right, here we go. This is a JavaScript file that contains the JavaScript definition of the pbkdf2 function. And remember, this is a normal function that is just included inside of the standard library of Node. You're going to find that the contents of this file looks very much like a JavaScript file that you and I might write. So at the very top, you'll find a bunch of require statements. In the body, you'll find a bunch of function declarations. And then down at the very bottom, you'll eventually see an export statement as well. So here's where the actual pbkdf2 function gets exported from this file. Let's go up a little bit, and we're going to find where this function actually gets declared. All right, so right about here on line 16 or so, you'll find the definition for pbkdf2. So if you and I were to require in this function and then run it from inside of our code base, this is the function that would get executed. Now this next part that we're going to go through is going to be just a little bit complicated because I'm going to very quickly kind of run through some of the source code that is executed anytime we call this function right here. But eventually we're going to end up on another part of the code base that starts to take us to like the C++ side of Node.js. So anytime you run this pbkdf2 function, it does a little bit of error checking, it does a little bit more error checking, and then eventually it calls _pbkdf2. So let's find the definition for _pbkdf2 and see what happens inside of there. So I'm going to scroll down, and then on around line 32 or so, you'll find the definition for _pbkdf2. Inside of here, you'll again see a bunch of error checking, error checking, just a bunch of error checking stuff. All the stuff is error checking. And then eventually, you'll see this block of code around line 72 or so. So right here, you'll see a call to another function called pbkdf2. And it takes in all the arguments that were passed to our current function and passes them to this pbkdf2. So this right here is where that hash is actually calculated. Essentially, nodejs takes all the inputs that you provide to this function and it forwards them on to the C++ implementation of this function. So this pbkdf2 thing right here, in all capitals, this is a C++ function. Let's see where this thing actually gets required into this file. If you scroll back up to the top, you're going to see around line 9 or so where we require in pbkdf2, and that's coming from a very unfamiliar looking require statement. So this says process.binding and then crypto. This line of code right here is how Node.js joins up the C++ side of its project to the JavaScript side. So I'm going to show you another diagram that's going to help flesh out the process of all the code that we've looked at so far. All right, here we go. So at the very top, again, is our JavaScript code. Then we went into the Node JavaScript side of the Node repository to look up how that function, pbkdf2, actually gets defined. We looked up a file inside the lib folder, which is all the actual JavaScript code works, and we found that eventually it looks like that pbkdf2 function is defined from something called process.binding. That process.binding thing is what connects the JavaScript world to the C++ world of the Node.js project. Let's take a pause right here. I know we're in the thick of things, but let's take a pause right here. We're going to come back in the next video, and we're going to start to explore what that process.binding thing does and how it joins up to the C++ side of the Node project. So quick break, and I'll see you in just a minute. In the last section, we started looking into the implementation of a function that is included in one of Node's standard library modules. We were able to find the function declaration inside the Node source code, and specifically was inside the lib folder. We saw that inside the JavaScript implementation of that function, there was eventually a call to a function that came from something called process.binding. This process.binding thing right here is what serves as an actual bridge between the JavaScript side of Node and the C++ side, which is where a lot of the internal work of everything that Node does for you is actually implemented. So a lot of your code relies upon, ultimately, C++ code. We left off at the process.binding statement. So from process.binding is a little bit of joining up to the C++ side. So we're going to, just for a second, we're going to skip over this V8 part right here, and we're going to go look up and find on the C++ side of the Node project where the pbkdf2 function is actually really truly implemented. So back over on GitHub, I'm going to go back to the root project directory. So all the way back up here at the Node project. And then this time, rather than going inside the lib directory, which is where all the JavaScript side of Node is placed, we're going to go into the src directory. So inside of here, I'll then find inside this file or folder, I'm going to find a file called, let's scroll down. Here we go, node_crypto.cc right here. Make sure you find the .cc file and not the .h one. So inside of the .cc file, you're going to find about 5,000 lines of C++ code. Yeah, 5,748 lines. So this is the entire crypto module right here. This is all the C++ code that the crypto module actually depends upon inside the C++ world. Inside this file, I'm going to scroll down immediately to the very bottom. So very down, all the way down to the very bottom. I'll then scroll back up just a little bit, and around line, here we go, 5704 or so, you're going to find what is essentially a C++ export statement. Now I know that you might not know C++ at all, and that's totally fine, but I think you can kind of get an idea of what's happening right here. This line of code is what takes the pbkdf2 function that is implemented inside of this C++ file and then somehow exports it as a function called pbkdf2. So this line of code right here is what was eventually getting invoked by that process.binding line. This is what somehow joined up the JavaScript world and the C++ world, and eventually made this C++ function right here available to you on the node side. Let's go find the actual declaration of pbkdf2 inside this file. So there are like 5,000 lines of code inside of here, so I'm going to just search for it. I'm going to look for void pbkdf2. And eventually, right about here we go. So this right here is where the actual real true 100% no goofing around implementation of the pbkdf2 function is. This is the actual function that calculates the hash for some value that you provide to the function itself. Now there's no need for us to go through all the C++ code inside of here, but I think that you can very quickly get the idea that, yep, it looks like whenever we run that JavaScript code, it ultimately relies upon some C++ code. Now the other thing you might be kind of curious about inside of here is where v8 and libuv come into play. If I go all the way back up to the top of this file, and then again scroll down just a couple lines, around line 85 or so, you're going to start to see a lot of kind of using statements right here. They're all using v8 : and then some name. So the purpose of the v8 project inside of all this node source code is to essentially act as the intermediary and allow values that are defined inside of JavaScript to be translated into their C++ equivalents. So all these using statements right here are importing the C++ definition of JavaScript concepts, like the C++ understanding of what JavaScript false is, or the C++ understanding of what an integer is, or null, or object, or string, or any of these other things. So this is where the v8 project actually comes into play. The v8 project is used to translate the nodejs values that you and I place inside of our different programs, like a Boolean or a function or an object, and translate it into their C++ equivalents. Now libuv is also used inside this file as well, although its presence is a little bit tougher to actually detect. So inside this file, I'm going to do another search, and I'm going to search for simply uv. Now when I search for uv, I'm going to immediately start to see things called like uv thread start to appear. And if I keep on searching, I'll see other things like uv work as well. So inside this file, libuv is used for a lot of concurrency and processing constructs on the C++ side. And that's actually the topic of great discussion that we're going to go into in just a little bit as well. Okay, so I know that this has been a very deep dive, and you might not know any C++ at all, but hopefully you now have a better sense of how whenever you and I write JavaScript code and require in node modules or node libraries, they are depending upon some JavaScript definition, which eventually kind of maps up to actual C++ implementation on the other side of the node project as well. And then on the C++ side, there's a lot of interoperability between the v8 project and libuv as well. So now that we have a better idea of how node modules are actually implemented, let's take a quick break. We're going to come back in the next section, and we're going to start to dive a little bit deeper into this libuv stuff. So quick break, and I'll see you in just a minute. In the last few sections, we got a better idea of how Node works, and now understand that Node internally uses the JavaScript v8 engine and the C++ library libuv to work correctly. In this video and the next few, we're going to start to dive into something called the event loop. The event loop is used by Node to handle asynchronous code that you and I write inside of our applications. Before going straight into the event loop, however, we're going to do a very brief detour and discuss something called threads. Once we understand what a thread is, we'll then go back over to the Node event loop. So in this video, let's get to it. We're going to start to discuss threads and what they are. All right, here we go. Whenever you and I run programs on our computer, we start up something called a process. A process is an instance of a computer program that is being executed. Within a single process, we can have multiple things called threads. You can picture a thread right here as being like a little to-do list that has some number of instructions that need to be executed by the CPU of your computer. This thread is given to the CPU, and the CPU will attempt to run every instruction on it one by one, starting at the top and then going down. A single process can have multiple threads inside of it. And in fact, I can actually very easily prove that to you by opening up the activity monitor on my personal laptop. So here's my activity monitor. It lists out all the different processes that are being ran on my computer. If you look at the bottom right over here, and I know the text is really small, but you can see that I've got about 250 different processes running right now. And inside there are about 1,400 different threads. So every one of these threads belongs to one individual process. One of the most interesting and important areas of study around threads is understanding something called scheduling. Scheduling refers to your operating system's ability to decide which thread to process at any given instant in time. So remember, your computer has a limited amount of resources available to it, and your CPU can only process so many instructions per second. This starts to get really relevant when we have many active processes and threads on our computer. Each one of these threads right here might have some urgent responsibility assigned to it. Like over here, we might have a thread that is responsible for making sure that whenever the user moves their mouse, the cursor on the screen moves as well. Or we might have another thread whose job is to make sure that keyboard typing or keyboard input shows up inside of some text input whenever the user types. So your operating system's scheduler over here has to look at all these different threads that are asking to be processed and figure out how to do some amount of work on each of them while making sure that they don't have to wait too long to be processed. Now that last part is really important. We want to make sure that urgent threads don't have to wait too long to be executed. So for example, if the thread in charge of moving the mouse around the screen has to wait like 5 seconds before it gets processed, the cursor will not move during that time, and the user is going to think that their computer is broken, which is obviously not good at all. There are a couple of different strategies that are used to improve the rate at which these threads can be processed. We're going to focus on two in particular that are going to end up being very relevant for us in the Node.js world. So in order to more quickly process threads or process more at one given time, we can first add in additional CPU cores to our machine. So if we have more than one core inside of our CPU, then we can easily process multiple threads at the same time. One thing I want to mention here is that technically one core can process more than one thread at a time through a process called multithreading, or you may have also heard it referred to as hyperthreading as well. But for right now, let's just say that more cores means more threads processed at once. The second thing we can do is more closely examine the work that is being done by each thread. So this is where things start to get really relevant for us in the JavaScript world. Let's imagine for a second that we have two threads here that are both competing for processing power. Thread number one has a set of instructions that want to read a file off the hard drive and then maybe count the number of characters inside of it. And then thread number two over here wants to multiply 3 by 3. The thing to keep in mind is that any time our computer tries to read data off of some type of medium, like a hard drive, we refer to that as input or output operations. And it always takes some non-zero amount of time. So during this I/O phase right here, your CPU is waiting on the hard drive to read some file and return its contents. And during that time, this thread number one, has absolutely nothing else to do. It's just sitting there waiting for the hard drive to get some information. Your operating system scheduler has the ability to detect this downtime, or this kind of pause between instructions. And it can decide to put thread number one on pause and then execute thread number two. And then as soon as thread number two is complete, it can go back over to thread number one and continue waiting on the hard drive to be read from the file to be read from the hard drive. Okay, so quick recap here. In this section, we spoke about some of the basics of threads. Threads are units of instruction that are waiting to be executed by the CPU. Deciding which order to execute these threads in is referred to as scheduling. Scheduling is controlled by your operating system. Two ways of improving the rate at which we process threads is to either add more CPU cores to our machine or to allow our OS scheduler to detect big pauses in processing time due to expensive input and output operations. So now that we understand a little bit more about threads, let's continue into the next section, and we're going to start to apply this knowledge to the node event loop. So quick break, and I'll see you in just a minute. In the last section, we got a very quick overview on threads. We're now going to take that knowledge and apply it to the world of Node.js. Whenever you and I start up a Node program on our computer, Node automatically creates one thread and then executes all of our code inside of that one single thread. Inside of this single thread, represented by this blue box right here, is something called the event loop. You can think of the event loop as being like a control structure that decides what our one thread should be doing at any given point in time. This event loop is the absolute core of every Node program that you and I run, and every program that you and I run has exactly one event loop. Understanding how the event loop works is extremely important because a lot of performance concerns about Node boil down to eventually how the event loop behaves. So essentially, if you understand this event loop, then you will be very well equipped to understand performance issues in Node as well. But there's a little bit of a problem in understanding it. Understanding the event loop is tough. It's not easy. There are many talks, many blog posts, many diagrams online to help you understand it, but it is just notoriously difficult to wrap your head around. Luckily, I have a solution. I got a solution to help you understand how the event loop works. So rather than looking at some really complicated diagrams, you and I are going to write some fake code inside of our code editor. So we're going to write completely fake code that doesn't work at all. This fake code, or kind of like pseudocode, is going to sort of emulate the event loop and how it works to make Node work. So let's give it a shot. We're going to create a new file inside of our code editor, and then we're going to add some fake code to it to walk through what the event loop does inside of our Node.js programs. So I'm going to open up my code editor, and then inside of here, I'm going to make a new file, and I will call it simply loop.js. So again, this is going to be entirely fake code inside of here. The code that we're going to write here is going to walk you through the series of operations that occur anytime we start up a Node program on our machine. So let's first start off by adding a comment at the top that sort of like pretends that we are starting up a Node application. So we might start a Node application by running a command at our terminal of something like node myfile.js. And then maybe a couple of lines after that, let's add another comment that says exit back to terminal. So in between these two lines right here, we're going to write out the entire life cycle of a Node application. Everything from starting it up to exiting back over to the terminal. Now, whenever you and I first start up a Node file or run Node and feed in some file like we're doing right here, the event loop does not actually immediately get executed. Instead, at the very start, like when we first invoke Node and feed in a file, Node takes the contents of this file right here, the contents of myfile.js, and it executes all the code inside of it. So all the code that you wrote. Let's write out a line of code underneath the comment that kind of pretends or symbolically indicates that the contents of myfile.js get executed by Node. So maybe we will write out something like myfile.run contents, like so. So again, there's no variable here called myfile. There's no run contents function. We are entirely just pretending with pseudocode that this is what is happening inside of Node.js. Now, after the contents of that file are executed, we then immediately enter the Node.js event loop. You and I are going to represent this event loop with a while loop. So underneath this line, let's write out a typical while loop, like so. This event loop right here, or this while loop essentially, is going to execute again and again and again. So the body of the while loop is going to run again and again and again. In the event loop world, we refer to this execution of the body as a tick. So every single time the event loop runs inside of our node application, we refer to that as one tick. I'm going to add a comment right above the while loop just to remind myself of that. So I'll say entire body executes in one tick of sorts. Now, as you and I very well know, every while loop that we ever write has to have some type of condition tied to it. We put that condition inside this set of parentheses right here. And whenever that condition returns false, the while loop is no longer going to execute. That same idea applies to the event loop as well. So every single time that the event loop is about to execute, Node first does a quick check to decide whether or not it should allow the loop to proceed for another iteration. If Node decides that the loop should not be entered or it should not be executed again, then the entire event loop gets skipped, or in our program, the body of the while loop gets skipped, and the program exits back to the terminal, like down here at the bottom. So to determine whether or not our while loop here, or our event loop, is going to execute, let's create a little helper function called shouldContinue. So I'm going to write out a helper function called shouldContinue. And then we'll call that from inside the condition area of the while loop. Now, as long as shouldContinue right here returns something truthy, the event loop is going to continue to run. But as soon as it returns something falsy, our loop is going to stop and the program will go down to the bottom of this file and essentially exit. So let's now take a quick pause. We're going to come back in the next video and we're going to start to talk about exactly what logic should go inside of the shouldContinue function. So quick break and I'll see you in just a minute. In the last section, we started writing out some pseudocode to model how Node's event loop works. We are now working on the shouldContinue function, which decides whether or not our event loop should continue running for another tick. So if shouldContinue returns true, our event loop is going to run for another tick. Otherwise, if it returns false, then the event loop will not run anymore and our program will exit back to the terminal. So inside of the shouldContinue function right here, nodejs does three separate checks. 3 checks to decide whether or not the event loop should continue for another iteration. We're going to start out by writing a comment that summarizes what each of these 3 checks are, and then we'll write out a little pseudocode to kind of simulate the check that really occurs. So the first check that Node does when it's deciding whether or not it should continue running our program is to look to see if there are still any functions that have been registered with setTimeout, setInterval, or setImmediate and still need to be executed. So we're going to write out check 1, any pending setTimeout, setInterval, or setImmediate. So if there's any functions that still have to be executed through setTimeout, setInterval, or setImmediate, then our program does not exit. It continues running for another tick. I'm going to assume that you are familiar with setTimeout and setInterval. You may have never seen setImmediate before, but it basically works in a similar fashion to these other two. We basically pass a function to it and it will be executed automatically at some point in the future. The second check that Node does to decide whether or not it should exit is to look to see if there are any pending operating system tasks. An example of an operating system task is something like an HTTP server listening to requests on some port. We'll talk more about exactly what an operating system task means in a little bit, but basically for right now, we're going to say that the second check that Node makes is to look if any servers are still listening for incoming requests. So check 2, any pending OS tasks, like maybe a server listening to some given port. The third check that occurs is to see if there are any long-running operations that are still being executed inside of our program. So this is going to be very similar to check number 2, but there is a distinct difference between the two that will go into great detail over time. An example of a long-running operation would be something like a function call inside the fs module to read some file off the hard drive. So I know that probably sounds very similar, almost identical to this second check right here, but it really truly is a different operation. So we'll go into a lot of detail on the difference between these 2 checks in just a minute. But for right now, I'm going to add a comment that says check 3, any pending long-running operations like fs module. And fs module here is referring to the file system module included with Node, which is used to read information off of our hard drive or write information as well. Okay, so we've now wrote out comments for the 3 checks that occur anytime Node decides whether or not the event loop needs to run for another pass. But right now, we only have comments. We don't have any actual code that kind of represents what's going on. So what does it really mean to say that we check for pending tasks or something like that? Well, I think that in all 3 of these cases, we can kind of imagine that there might be an internal array of sorts inside of our Node program that keeps track of any of these pending tasks that might be created. So maybe any time that our JavaScript code creates a new set timeout or makes a new call to the fs module, maybe an entry is added to some array to keep track of that task that is currently being executed. So let's create 3 arrays above our myfile.run contents call right here. And it's going to simulate kind of like bookkeeping stuff that's going to allow us to very easily check in the future to see if we still have any pending operations going on. So I'm going to write out 3 arrays. I'm going to call the first one pending timers, then pending OS tasks, and then finally pending operations. Then back down inside the should continue function, we can add in some imaginary code that would look at these 3 arrays right here and check to see if there are still any pending operations in any of them. And if there are still any pending operations, then we'll return false from should continue, or excuse me, we'll return true. Otherwise, if there are no more operations for us to wait on, then we'll return false and our program will exit. So to very easily check to see if there are still any remaining tasks inside these 3 arrays, we can do something like return pending timers.length or pending OS tasks.length or pending operations.length, like so. So now if any of these 3 arrays still have any pending operations or any pending tasks inside them, our should continue function is going to return true. Otherwise, if there's nothing else for us to wait on, the should continue function right here is going to return false, and our while loop will exit and we'll eventually get kicked back over to our terminal. Now internally, Node is going to automatically detect when our JavaScript code that you and I write sets up something like a set timeout call or issues a new call to the fs module. These automatic detections occur even during that initial run of our my file right here. So these arrays are created as soon as we create our program or we start our program at the terminal. And then these arrays get records added to them as soon as you and I start to actually call set timeout or start up servers or work with the file system module inside of the code that you and I write. So I'm going to add a comment right above this line just to remind myself of that. I'll say new timers, tasks, operations are recorded from my file running. So this actually makes a lot of sense. When you and I run a Node program from the command line and say set up a HTTP server, that Node program does not instantly close and go back to the terminal because we set up a pending OS task. We told our server, or we told our program to listen to some port on our machine, and that adds a new task to this kind of imaginary array that exists inside of our program. Okay, so we've now established what causes the event loop to begin and then continue running. So let's pause here, and then we're going to continue exploring the internals of the actual event loop, or what goes on inside this while loop right here, in the next video. In the last section, we finished up our should continue function, which decides whether or not our event loop is going to run for 1 additional tick. We're now going to move to the body of our event loop. We're going to write out a series of comments that explain what occurs during every single tick. So these steps are occurring very, very quickly again and again and again. Let's write out the first step that occurs inside the event loop. So the first thing that happens here is Node looks at pending timers. That's what we called it, right? Talking about this array up here, pending timers. and sees if any functions are ready to be called. So the very first thing that occurs is Node looks at that array of pending timers, and it looks at all the different functions that have been passed to set timeout and set interval. If any of those timers have expired, then Node calls the relevant callbacks associated with each one. So that's step number one. Let's also add in a little one here just to keep track. The next thing that happens is very similar to the first step. So for the second step here, Node looks at pending OS tasks and pending operations and calls relevant callbacks. So in the second step, Node will look at that collection of all the different tasks and operations, and if any of these things have been completed or any new events have been triggered, then Node executes the relevant callbacks. Examples of these would be like the same examples that we laid out before. So for example, if some request comes into some port that a server is listening on, or if some file is successfully retrieved off of our computer's hard drive, then during this stage, Node will detect that those things have been completed, and it will call the relevant callbacks, like the callback to receive a file that's been fetched, or a callback to handle an incoming request. So you can really consider these first two steps right here as where Node does the bulk of its work and handles all the relevant callbacks. Now moving on to the third step is where things start to get a little bit more interesting. During step 3, Node actually pauses execution temporarily. So we say pause execution. And during this pause, Node just sits around and waits for new events to occur. So Node just sits here, it pauses, and it says that I will continue whenever some number of events occur. And that is whenever a new pending OS task is done, whenever a new pending operation is done, or whenever a timer is about to complete. So during this pause phase, Node decides that it's not going to just run through the event loop as fast as it possibly can. Remember that if you and I wrote out a while loop inside of JavaScript code and wrote in like say while true right here, something like this, that while loop would execute as fast as it possibly could. And that's not actually what occurs inside the event loop. Inside the event loop, this pause during step 3 just sits around and says, you know what, I've got no other work to do. I'm just going to wait until I see that a new pending task has been completed, like a new request has come in on some port that we're listening to. A new pending operation is completed, like we fetched some file off the hard drive, or a timer for one of the set timeouts and set intervals is about to expire and the relevant function needs to be called. So we just sit around and wait for that stuff to happen. Then, once that pause is complete, because we presumably see that something is about to occur, we then continue with the last two steps inside of the event loop. Step number 4 is very similar to step number 1. Up inside step number 1, you'll notice I had said that we're checking to see if any functions related to pending timers are called. And I used the words, I didn't actually write this out, but I had said set timeout and set interval. So this first step up here is about set timeout, set interval. During step number 4 down here, Node again looks at pending timers. So again, look at pending timers. But in this case, Node does not care about set timeout and set interval function calls. It only looks for functions that have been registered with set immediate. And remember, set immediate is very similar to set timeout and set interval, just in case you've never used it before. So look at pending timers, call any set immediate. And then finally, for step 5, and this one might be a little bit surprising, step 5 is to handle any close events. Now this one is a little bit harder to explain. So let me show you a very quick example. I'm going to open up a separate file here and I'll write out a very quick example for you to see. Okay, so an example of this would be if we use something like a standard object in the Node library that events a close event. Now one particular event or one particular object that does this is a read stream. If you've never worked with a read stream before, that's totally fine. Let me just write out the example and I think you'll very quickly understand what we're talking about. So if we had a read stream we can register an event to run whenever this thing is about to close. And during that event trigger, we could do some cleanup work. So we might do a console log of like cleanup code. So we can listen to this close event, and anytime the event loop is about to finish, we can run some amount of cleanup code that maybe terminates any running servers or terminates any open files we have open or something like that. Essentially, this last step inside the event loop is about just handling cleanup code and cleaning up after ourselves and making sure that we don't have any dangling loose ends inside of our program. Okay, so that's it, the 5 steps that are executed during every execution of the event loop. This occurs during every single tick that occurs. And probably the most important thing to understand here is step number 3, the fact that we wait around and just wait for some amount or some event to occur rather than running through the event loop as fast as it possibly can. So that now that we've seen these 5 events that occur during the event loop, let's continue in the next section, and we're going to start to discuss some odds and ends around the event loop and also play around with some real code. So quick break, and I'll see you in just a minute. In the last section, we finished up going through the 5 different steps that occur during one tick of the event loop. In this section, we're now going to move on and start talking about some very interesting things about the event loop. The first thing we're going to discuss is to clarify a very common misconception about Node. So here's the misconception. You may have read online from time to time that Node is single-threaded. That's what people claim. People say Node is single-threaded. I even showed you a diagram a few minutes ago that clearly declared that the event loop uses just one thread. However, that's not the full story. The truth is much more complicated. So in this section, we're going to start to investigate whether or not Node is truly single-threaded. All right, so here's kind of going to clarify what's going on here. We're going to investigate this claim a lot, but here's the first taste of it. So the Node event loop that we just went through is truly single-threaded. When we start up a program with Node, a single instance of the event loop is created and placed into one thread. Now that's commonly seen as kind of a bad thing because it means that our program can only run on one core of our CPU. So if we have many cores inside of our CPU on our computer, then Node is not going to automatically take advantage of those. So in other words, our program might not run as fast as it could be because it's limited to one single thread. However, some of the functions that are included inside of the standard library of Node are not actually single-threaded. In other words, some of the functions that are included inside of Node that we run outside of our event loop and outside of that single thread. So simply declaring that Node is single-threaded is not absolutely true. The event loop uses a single thread, but a lot of the code that you and I write does not actually execute inside that thread entirely. So in this video, we're going to start to look at a couple examples of that. Now I'm not going to show you any diagrams, and I'm not going to give you any long speeches to convince you of how this works. Instead, you and I are going to write some code. We're going to then execute it at the command line, and you're going to get some very real proof that not all of Node is truly single-threaded. So let's open our code editor back up, and we're going to write a little bit of code. All right, inside my code editor, I'm going to create a new file, and I'll call it threads.js, like so. Inside this file, you and I are going to require in the pbkdf2 function. That's that hashing function that we looked at in the crypto module just a little bit ago. In particular, we're going to try to run that function, and we're going to benchmark exactly how long it takes to run on our computer. So let's first start off by requiring in crypto at the very top. And remember, this is a standard library that is included with Node. We're then going to pick off the pbkdf2 function and execute it inside this file. So I'll say crypto.pbkdf2, and then we're going to pass in a couple arguments here. Now, you don't really need to know exactly what this function is doing because I know I haven't really clearly told you what it's doing. All we're doing is using this function to kind of do some expensive work inside of a program. So it's going to take this function a while to run. and we'll be able to benchmark the amount of time that it takes to run and use that to detect whether or not Node truly is single-threaded. So I'm not going to tell you too much about the arguments here. We're just going to throw the arguments in and move on. So as the first argument, I'm going to pass in a string of A. For the second, I'll pass in a string of B. For the third argument, and this one actually is important, so for this argument, please make sure you do the same thing as I'm going to put in 100,000, like so. So make sure you've got 100,000 exactly. Then as the fourth argument, I'll put in 512. For the fifth, I'll put in a string of SHA-512. And then as the last argument, I'm going to provide a callback function. Now the callback function right here gets invoked after the pbkdf2 function has successfully executed. So this function takes quite a while to run. In total, on my machine, it's probably going to take about 1 second to run. And to handle that duration or that amount of time that it takes to execute, we get this callback function that gets called after this hash has been successfully computed. Again, we don't really need to know what the function itself does. Basically, we call the function and then eventually the callback is going to be executed. Okay, so let's take a quick pause right here. When we come back in the next section, we're going to add in a little bit of code to benchmark how long it takes this thing to run. So quick break, and I'll see you in just a minute. In the last section, we created a new file that we're going to use to benchmark the pbkdf2 function. And we're going to eventually use this to detect whether or not Node truly is single-threaded. Now we've got our function call inside of here. So the next thing we need to do is add a little bit of code to benchmark how long this thing takes to run. To benchmark it, I'm going to first declare a new variable outside of the function call. I'm going to declare a new variable called start, and this is going to record the time at which we start our call to the pbkdf2 function. So I'm going to say start equals date.now, like so. Then inside the callback, I'm going to add a console log, and this thing is going to log out exactly how long it took from recording the start time to getting inside the console log. So I'll say console.log. I'm going to pass in a string with 1, like so, because we're going to eventually have multiple console logs inside this program. And by adding in the little 1 right here, I'll know which console log we are seeing inside of our terminal. And then as a second argument, I'll take the new time, so like the current time, with date.now, and then I'll subtract start from it like so. So we take the start time, we call the function, and then when the callback is triggered, we take the new current time, we subtract the old time, and we should get out how long it took in milliseconds to print out or to calculate this hash value. So let's save this file. We'll go run this at the terminal, and we'll see how long it takes to calculate a hash. So back in my terminal, I'm going to make sure I'm inside of my directory with the threads file, and then I'll run node threads.js, like so. And when I do so, you'll see that I print out 1 colon and then 1073. So that means it took 1000 milliseconds, or just about 1 second, to run that pbkdf2 function. Okay, that's a good benchmark. We now know how long it takes to calculate exactly 1. I'm now going to go back to my code editor, and I'm going to take this entire function call right here, and I'm going to duplicate it down underneath. So I'm going to copy it, and then on the next line down, I'll paste it, and I'll make sure that I update the console log right here to 2 as well. Now before we run this back at the terminal, I want to make 2 things extremely, extraordinarily clear here. Okay, 2 things that are absolutely critical to understand about the code we've written inside this file. First off, when we run this file, both functions, both this call and this call, are going to be invoked at more or less the exact same time. So this code is not going to wait for the first call to finish up and get to this console log before starting the second one. That's not what's happening. The instant we execute this file, they are both executed at the same exact time. Now the second thing to be aware of here is that we are not modifying the start variable at all. So each console log that we're going to eventually see, like console log 1 and console log 2 right here, are going to be the exact amount of time that it took from starting our program to the time that it took for each function call to end. So with that in mind, let's go back to the terminal, and we're going to run this file again and see what happens. Okay, so back at the terminal, I'll run node threads.js. Now, when I run this, you're going to notice that my time is slightly above what it was before. So originally I got about 1073, and now I'm getting 1150 and 1159. But chances are you are seeing two times that are very, very close to your original time. Chances are. It might not be the case, but chances are you're going to see two times that are very close to the original ones. The reason that my two times right here are a little bit above or a little bit elevated is just because I'm running some screen recording software right now that uses up a lot of CPU on my computer. But anyways, the point is that chances are we're going to see two times or two benchmarks that are extremely close in time to the original one. Now, just to make sure that you really understand what's going on here, I want to show you a couple of diagrams that are going to help you understand the significance of this result right here, okay? All right, so a couple diagrams. Here we go. All right, so first off, we got this diagram. So this is a diagram of what I would have expected to see if Node was truly single-threaded. Remember that a thread presents a linear series of instructions to our CPU. So the CPU has to follow them all in order of the order that we present them in. Now we know that one call to PBK df2 takes exactly 1 second. So like 1 second right here. So with two function calls, if this really was a single threaded system, I would have expected this entire process to take 2 seconds total. We get 1 second for the first call. That completes. We should see a console log. And then after 1 additional second, we should see a second console log appear. Let's take a look at a diagram that's going to make this expectation right here much more clear. And again, this is talking as though we are assuming that Node is single-threaded, and it's not quite. Okay, so second diagram, just to clarify what we would expect if Node really was single-threaded. So I would have expected that we would have started our program at time of 0 seconds right here. The first call to PBK-df2 would have taken 1 second, and then as soon as that was complete, we would then start up the second call, and then at 2 seconds, the second call would be complete as well. However, both these diagrams that I just showed you clearly was not what occurred. This is not what actually happened when we ran our code. We very clearly saw that both these logs occurred at basically the same time, and it took just about equal to the original run of our threads function, where we were only doing one single hash. So let's take a look at a diagram of what really happened. So here's the reality. The reality was that we started up our program at 0 seconds up here, and then it took exactly 1 second for both of those function calls to get to the callback. So clearly, this is indicating that something is happening to indicate that we are breaking out of a single thread setup with Node. Because if we only had one single thread, we would have seen the first function call complete and then the second one start up. So let's pause right here, and we're going to start to investigate why this is happening in the next section. In the last section, we saw some evidence that a function call to PBK-df2 is not actually single-threaded. In this section, we're going to expand on this example a little bit and figure out why we are seeing this behavior. First, let's look at a diagram of what's actually going on with a PBK-df2 function behind the scenes. So remember, we dove into the source code of this function a little bit ago. And as we saw, the PBK-df2 function has both the JavaScript implementation, but it actually delegated all the work to be done to the C++ side. So that's where the actual hashing process took place. We also saw very briefly in that C++ file that there seemed to be some references to the Libuv library, which, as you'll recall, gives Node some better access to the underlying operating system. The Libuv module has another responsibility that is relevant for some very particular functions in the standard library. So for some, that's the keyword here, for some standard library function calls, the Node C++ side and Libuv decide to do expensive calculations outside of the event loop entirely. Instead, they make use of something called a thread pool. The thread pool is a series of 4 threads that can be used for running computationally intensive tasks, such as the PBK-df2 function. By default, Libuv creates 4 threads in this thread pool. So that means that in addition to the thread used for the event loop, there are 4 other threads that can be used to offload expensive calculations that need to occur inside of our application. Many of the functions included in this node standard library will automatically make use of this thread pool. And as you might imagine, the pbk df2 function is one of them. Now the presence of this thread pool is very significant. Obviously, from the standpoint of people always saying, oh yeah, node is single-threaded, node is single-threaded. Well, clearly it's not truly single-threaded because there are other threads that node uses for doing some computationally intensive tasks. You see this thread pool here because if our event loop was responsible for doing this computationally intensive task, that means that our node application could do absolutely nothing else while we were running the pbk-df2 function. Remember, our CPU runs all the instructions inside of a thread one by one. So if our thread had some line of instruction inside of it that said, run this code that takes 1 second to run, then that's pretty much it. We have to wait 1 second for that code to run. So by using this thread pool right here, we don't have to wait that 1 second, and we can do other things inside of our event loop while that calculation is occurring. Okay, so now that we have seen this thread pool right here, let's take a quick pause. We're going to come back in the next section and we're going to modify our file just a little bit, and it's going to allow us to actually detect the presence of these 4 threads inside the thread pool. So quick break, and I'll see you in just a minute. In the last section, we spoke about how Libuv provides a thread pool for offloading work to be done on very expensive function calls. In this section, we're going to modify our threads.js file and start to detect the presence of these 4 threads that are created for us automatically. So I'm going to go back over to my code editor where we have our 2 calls to pbk df2. I'm going to copy the bottom call here, and then I'm going to duplicate it down a couple of times. So in total, I want to have 5 separate calls to pbk df2. So here's console log number 3, and I'm going to update the console log. Here's number 4, and I'll update the console log to 4. And here's number 5, and I'll update the console log to 5 as well. Now I'm going to save this file, and I'll go back over to the terminal. I'm going to run this file again, and I'll see what happens. So back over at the terminal, I'll run node threads.js again. All right, so take a look at the results here. Do you see that little pause? Let me run this again. So we get the first 4 results, a pause, and then the 5th result suddenly appears. So this result right here is extremely interesting, and we can use these results to really divine some information about the thread pool and how it works. Now, one quick note, depending on your machine's CPU, you might see some different results here from what I see. So if you have a different machine than I have, you might see different results, and that's totally okay. Let me explain to you what's going on with my computer, and then you can kind of extrapolate what's happening to your own machine as well. So let's take a look at a diagram that's going to help explain what's going on. All right, here we go. Okay, so again, the first 4 calls took 2 seconds to complete, and then the 5th call took 1 additional second. There's really 2 interesting things to note here. First, notice that the first group up here all took the exact same amount of time, and it took roughly double what it had taken previously. So previously it took 1 second to get through the 2 calls, but now it appears to be taking 2 seconds. The second thing that I want you to note is that the 5th call over here only took 1 additional second. So that's very interesting behavior. Let's try to figure out why we saw the change in timing with the first group that ran, and then only 1 second to complete the 5th call. All right, so I'm going to show you a diagram of my computer. So this is a 2015 MacBook Pro, and by understanding the hardware that's inside of my computer, we'll have a better idea of why we saw that differing timings inside of all those function calls. So I'm using a MacBook Pro that was made in 2015. This computer has a dual-core processor, so 2 separate cores. Let's first consider the original program that we wrote, where we had just 2 calls to pbk df2. So in that case, the first call was taken, and we can kind of imagine that maybe it got assigned to the first thread in the thread pool. That thread, we can again imagine that maybe this thread right here got assigned to running on core number 1. Then the second call to pbk-df2 maybe got assigned to the second thread, and maybe this second thread got assigned to my second core. So we saw that these 2 calls each got assigned to 2 different cores in my machine, and they both took more or less exactly 1 second for each core to finish the hashing function call. So let's now take the similar diagram, but apply it to the case that we just ran this in with the 5 function calls. All right, so here we go. So in this case, the first 4 calls each got offloaded to one thread that existed inside the thread pool. Now, here's where things start to get a little bit different. Remember how we had said when we spoke about threads much earlier that we can kind of get some level of concurrency with threads because our CPU has access to multithreading or hyperthreading, which allows it to kind of process more than one thread at once. When we just very briefly mentioned that. But that's actually the behavior that we're seeing right now with these 4 separate calls. So the first 4 calls to PBK df2 each get assigned to their own individual thread. Then thread number 1 and thread number 2 get assigned to CPU 1, or core number 1, excuse me, and thread 3 and 4 get assigned to core number 2. Our 2 cores, or my 2 cores, are only able to process these 2 threads at the same time thanks to multi-threading technology in my CPU. So because I've got multi-threading enabled, I can process more than one thread at the same time. However, each core still had to do twice the amount of work. It just had to do twice that amount of work at the same time, which is why we saw that it took roughly twice as long to calculate the hashing value for these first 4 values. Because at the end of the day, even though I have multi-threading enabled, all that enables my CPU to do is process more threads at once. It doesn't actually speed up the processing, it just allows for some amount of concurrency inside of the work that I'm doing. So we saw those first 4 calls get processed. They took roughly double the amount of time. And then once that was all complete, and those first 4 tasks were done, oops, let's undo that. Then Node was able to finally move on to the 5th function call. So maybe that one got assigned to thread number 4, and then thread number 4 maybe got assigned to core number 2. And because now core number 2 was only processing 1 hashing function call, this time around it took only 1 second. Okay, so I know that this has been some confusing stuff, but let's take a pause right here. We're going to come back in the next video and we're going to continue exploring this idea of threads in the thread pool by writing out some more experimental code. So quick break and I'll see you in just a minute. In the last section, we spoke about what happened when we lined up 5 calls to PBK df2. The first 4 calls were each allocated to their own individual thread in the thread pool. And then groups of 2 threads were each assigned to each of our cores. Now remember, these threads can technically run at the same time, but they still have to do just as much work as they did previously. And that's why we saw it took twice as long for all the hashes to complete, because it always takes 1 second to calculate 1 hash. So if we have 4 hashes, but each core is taking twice as long to do that work, it's going to take 2 seconds total. We're now going to move on a little bit and figure out how we can work with and customize the thread pool that we see right here. So I'm going to go back over to my code editor and we're going to add in a little bit of code to play around with a number of threads that get created anytime we start up our program. So back inside of my code editor, I'm going to go up to the very top line, and above that require statement, I'm going to update a environment variable. So I'm going to say process.env.uv threadpool size, and I'm going to set the value of that to be equal to 2. So this is going to tell libuv that whenever it creates its thread pool, it should only create 2 threads inside there. Now I'm going to save this file and I'll rerun it at the terminal. But before I do, I want to ask you, just pause the video for a second. I want you to guess as to what effect this is going to have on our benchmark. So just think about it for a second. Okay, hopefully you've got an idea. So let's run this code and see what happens. So now we see that they are being completed in groups of 2. Well, that's interesting. Let's take a look at a diagram that summarizes what's going on. So here's our diagram. So now we have 2 of these functions, or 2 hash calls being executed at a time, because we only have 2 separate thread pools. So the first call gets assigned to thread 1. The second call gets assigned to thread number 2. Thread number 1 probably gets allocated to core number 1. Thread number 2 probably gets allocated to core number 2. And now we're back to the situation where each core only has to do 1 hash at a time. So we're back to the hashing only taking 1 second. After the first 2 hashes are complete, the next 2 calls are loaded into thread number 1, and thread number 2. Again, that takes 1 second. And then finally, after that's done, finally the 5th call can be loaded in as well. So hopefully that gives you a better idea of how we can customize the thread pool and see what happens when we decrease the number of threads that are available. Now let's do the opposite, just for fun. Let's reverse. Let's try increasing the number of threads that we have available. Let's try going up to like 5, like so. So again, I'm going to save this file, and we'll go back over to the terminal and save this and run this again. And again, I want you to kind of guess as to what's going to happen. Okay, let's run this again, and let's see. So now this time, it looks like it took quite a while, but when it eventually resolved, it took a total of about 3 seconds and everything completed at the exact same time. So let's again look at a diagram. All right, so now here's the situation we're in now. So we've got thread 1 through 5. We have an equal number of threads to the number of hashing function calls. So each hashing function call instantly gets their own thread assigned. And now this time, we see that thread number 1, 2, and maybe 4 and 5 go to core number 2 like so. I know you can barely see these arrows, but I think you get the idea. And then you might have thought that like maybe one core was going to take slightly longer because it had to get the 3rd thread, right? So maybe core number 2 also had to do thread number 3 over here. And so you might have expected core number 2 to take slightly longer. But in reality, our CPU can use all the cores inside of it to juggle work between multiple threads. So when I say that, oh yeah, core thread number 1 gets assigned to core number 1, that's not entirely accurate. This OS scheduler right here kind of decides how to juggle all the work in total behind all the cores that are available. So at the end of the day, all 5 threads get roughly equal amounts of CPU time at the same time. And that's why we saw everything complete at the same time. But this time, it took about 2.5 seconds, or maybe right above that. A little bit longer than 2.5. Again, if I wasn't running my video recording software, this should have taken about 2.5 seconds. Because just as before, we have only 2 cores available. By default, it takes 1 core 1 second to process 1 hash. So when we have 5 hashes at the same time, it's going to take 2 cores, 5 divided by 2, 2.5 seconds to calculate. So again, my timings didn't quite line up with that, but if I wasn't recording my screen right now, it would have taken just about exactly 2.5 seconds. Okay, so in this section, we spoke about the existence of the Libuv Threadpool that is used for expensive calculations. So you're probably really curious about what functions in the node.js library actually make use of this Threadpool and about how you can use the Threadpool for your own personal code. So let's start to answer those questions in the next section. In the last section, we updated the number of threads that are created inside of our Threadpool and observed what actually occurred. In this section, we're going to address a couple of questions you've probably got around the existence of this Threadpool. So I'm going to pull up a couple of questions and we're going to go through each one. Here we go. Okay, so on the left-hand side, we've got a question, and on the right-hand side, a possible answer. So the first question you probably have, and this is probably the most obvious one, can we use the Threadpool for our own personal JavaScript code? Or can only certain node.js functions, like the pbk df2 function, make access to it? And the answer to that is that you and I can write JavaScript code that makes use of that Threadpool. And we'll see exactly how to do that later on in a couple of videos. So yes, we'll figure out how we can run our own JavaScript code in separate threads. The second question you might have is, what functions inside the node standard library actually make use of it? So this one is a little bit more complicated. And I cannot give you a very distinct answer of exactly which functions are executed inside that Threadpool and which are not. And the reason for that is that a lot of it depends on what operating system you are on. So depending on whether or not you are on Windows or a Unix-based system, you're going to see different functions getting access to the Threadpool. Now the one common thread is that all of the file system module functions, like every function inside the file system, makes use of the Threadpool, no matter what operating system you're running. Now the final question you might have here is, how does the Threadpool stuff actually fit into the event loop? Remember, we wrote out some kind of like test code a little bit ago, or pseudocode, to simulate how the event loop works. You might be curious, what presence does this Threadpool have in all that pseudocode that we wrote? Well, you might remember that we had that pending operations array back inside of our pseudocode example. So here's our Threadpool thing. And at the very top, we had defined that pending operations array right here. And then any time that we wanted to check to see if our event loop should continue running, we check to see if there were any pending operations left inside that thread pool. So this pending operations thing right here essentially represents code that is being executed or tasks that is being executed inside the thread pool. So long as that thread pool still has some code inside of it or some tasks lined up for it to run, our program is going to continue to execute the event loop. And then you might recall that inside the event loop itself, at step number 2 right here, we had said that node looks at the pending operations array and it calls any relevant callbacks. So after we finish calculating one of our hash values inside of one of those threads, the callback that we had registered with the pvk-df2 function is then executed when we go through step number 2 right here. So that's how everything kind of relates back to the event loop. Okay, so now we got some of these probably common questions out of the way. Let's continue in the next section, and we're going to start to dig into that other array that we have not spoken about. Remember up here, we also had that pending OS tasks thing. So quick break, and we'll start to dive into what this array up here meant as well. So I'll see you in just a minute. In the last couple of videos, we examined the thread pool that is automatically created by Libuv anytime we start up a node program. That explained the presence of this pending operations array inside of our event loop. In this section, we're going to start to look at the stuff that's going on behind the scenes to explain this pending OS tasks array right here. We're going to take a very similar approach to what we did previously. So we're going to first start off by writing out a little program that is going to run some code that's going to benchmark a function inside the node standard library. We're going to benchmark it, and then we'll be able to kind of derive some understanding of what's actually going on behind the scenes. So we'll first get started by creating a new file that's going to house the benchmarking code. Inside of my code editor, I'm going to make a new file called async.js. So the benchmark that we're going to do is to fetch the Google homepage. We're just going to make a request over to Google. We're going to get their homepage, and then we're going to calculate exactly how long that takes. We'll then do that process multiple times, and we can use that to kind of figure out exactly what's going on behind the scenes. So at the top, we're going to require in the HTTPS module to make the actual request. If you've never used this module before to make a request, don't sweat it. It's going to be relatively straightforward. Immediately after we require that module in, we will then store the starting time of our benchmark with a date.now. And then immediately after that, we'll make our actual request. So I'm going to write out https.request. The first argument is going to be the URL that we want to make our request to, which in this case is https://www.google.com, like so. And then the second argument is a callback function. Now the argument to the callback function I marked as res, but this is not like when you're using Axios or jQuery. This is not the entire response object right here. Instead, this is an object that emits events as we receive data from Google servers. So it's a little bit more complex and low level than some of the networking libraries that you might have used before. Basically what that means is we're going to have to write some fancy looking code inside this callback. I'm not going to talk about what this code is doing too much because honestly it's not really at all relevant to what we're doing right now. So I'm going to say res.on data, and then as a second argument I'll pass in an empty function, and then I'll also do res.on end, and I'll do another arrow function, but inside this one we'll do our actual benchmarking. So I'll say console.log date.now minus start time. And then one last line of code inside of here. After the request.call closing parenthesis, so like right here, to actually get this request to be issued, we have to call .end on it like so. Now when I save it, my code jumps on the screen because I have a code reformatter. But basically just don't forget to put on that .end. All right, so let's now flip back over to our terminal. We're going to run this file and see how long it takes to make this request. So over at the terminal, I'll do nodejs, and I see that it takes about 270 milliseconds, maybe plus or minus a couple, to make the request over to Google servers. And it looks like I'm kind of around maybe 240 now. Okay, so this looks good. let's pause right here, and then we're going to use this code to do some more benchmarking in the next section, and that's going to give us a better sense of what Node is doing internally to handle network requests. So quick break, and I'll see you in just a minute. In the last section, we wrote a small file to make some HTTP requests for us, then ran it and saw that it took about 240 milliseconds to make a single request over to Google. We're now going to add in some more requests to this file, and when we do so, we're going to see some evidence that some of the functions in the Node standard library don't seem to use the same kind of Threadpool that our hashing function did previously. So inside my async function, back over here, I don't really want to copy paste this entire code block down like 6 times. So I'm going to wrap this request inside of a little helper function that I'm going to call simply doRequest, like so. So now rather than doing a whole bunch of copy pasting, at the bottom of the file, I will instead call doRequest a couple times in a row. And maybe that's good like so. Okay, so let's save this file, and now we're going to go run this file again at our terminal. So back over at the terminal, I'll again do nodejs. And now we see some very interesting behavior. Notice how it appears that all 6 calls appear to be completed at the same exact time. This is distinctly different behavior than what we saw previously with our Threadpool. So remember, by default, the Threadpool has 4 threads, which means only 4 tasks can be processed at a time. But in this case, we had 6 tasks all completed simultaneously. So what's up? What's going on here? Well, let's take a look at a quick diagram. Oh, let me move this thing around. There we go. All right, much better. So what we're seeing here is more evidence of libuv in play, but it's not related to our Threadpool. So just as the Node standard library has some functions that make use of libuv's Threadpool, it also has some functions that make use of code that is built into the underlying operating system through libuv. So in this case, libuv sees that we are attempting to make an HTTP request. Neither libuv nor Node has any code to handle all of the super low-level operations that are involved with a network request. Instead, libuv delegates the request making to the underlying operating system. So it's actually our operating system that does the real HTTP request. Libuv is used to issue the request, and then it just waits on the operating system to emit a signal that some response has come back to the request. So because libuv is delegating the work done to the operating system itself decides whether to make a new thread or not, or just generally how to handle the entire process of making the request. So because the operating system is making the request, there is no blocking of our JavaScript code inside of our event loop or anything else inside of our application. Everything or all the work is being done by the operating system itself, and we're not touching the Threadpool at all in this case. Okay, so let's pause right here, and we're going to continue the next section and talk about how this relates back to our event loop in the next video. In the last section, we spoke about an additional avenue used by nodejs to get code executed. So some function calls in the standard library are delegated to the underlying operating system and ran entirely outside the event loop. Now I again imagine that you have some follow-up questions about this process. So let's look at 2 possible questions that you might immediately have. All right, here we go. So 2 possible questions that you might be thinking about right now. So the first one, you might be curious what functions in the Node standard library use the operating system's async features. So this is a very similar answer to the one that we had previously for that Threadpool. A lot of this stuff is very specific to the operating system that you're running on, and you can't really depend upon one function always being executed through the operating system on one computer or a different way on the other one. In other words, don't try to detect or plan around this stuff ahead of time. Now, almost everything inside the networking library, like say making requests or receiving requests or setting up a listener on some port, almost all that stuff is handled by the operating system, regardless of what operating system you're using. So that's the one solid answer I can give you. Now, the second question might be, okay, hey, we now know about this async stuff tied to the operating system, but where does that fit into all the event loop stuff that we were talking about earlier? So as you might imagine, That stuff is all related to that pending OS tasks array that we had created back inside of our pseudocode file. So here's our loop file over here. Inside of here, we had that pending OS tasks array. So we can kind of imagine that when node runs, it creates some type of data structure that represents all the pending requests or networking or whatever else tied to the underlying operating system. As long as there's still some active request or some active operation inside that array, node is going to continue running. And it's going to always return truthy on this should continue function right here, which means we're going to continue iterations through our event loop. And then as soon as all those underlying operating system calls are complete, well, now the event loop has nothing else to do, and we exit back over to our terminal. So that's why when you start up a server and say app.listen on port 3000 or whatever, that's exactly why your application continues running in the terminal and does not immediately exit back to the command line. Okay, so we've now spoken about the event loop quite a bit. Let's summarize some of the main things to know about it inside the next video. So quick break and we'll do a review in just a moment. In the last dozen videos or so, we've tackled some pretty complicated topics. In this video, we're going to take a quick pause and review everything that we've covered so far. Now I've got a summary diagram that's going to summarize exactly what happens when you start up a node program on your local computer. So everything starts off up here at the top when you run the command node index.js or whatever file you might be running. When you run that command, node immediately executes and processes all the code inside of that file. Now, one thing you might be curious about during this phase as well is require statements that you have inside that file. The instant you boot up node, all the code inside that file and any required files as well are all executed. So if your index.js file has some require statements, those are instantly required in and executed as well. Node then enters our event loop. The event loop has one overarching big question. It says, do we still have any work to do? Do we have any timers? Do we have any operating system tasks for doing networking or similar tasks? Or do we have anything still running inside of our Threadpool? If we don't, then our program instantly exits and there's nothing else for us to do. But if we do still have some amount of work to do, then we go through a series of a couple of different steps. We first check to see if there are any set timeouts or set intervals that need to be executed. Next, we check to see if any callbacks are ready to be called, tied to anything related to operating system tasks like networking or anything related to our Threadpool. And this is probably the vast majority of code that you and I write inside of Node applications. Next, the event loop just pauses and sits around waiting for stuff to happen. So it waits for some task to complete, or it waits for some timer to come up, or whatever else it might be waiting for. After that, we then run any set immediate functions that have been defined inside of our code. And then finally, we handle any close events, which allow us to do some amount of cleanup inside of our application. And then of course, the last thing is to go back up to the top and repeat the entire process all over again. Remember that we refer to one execution of the event loop as a tick. So you'll see that terminology quite frequently in a lot of Node documentation. All right, so that's a quick review, but we still have a lot of topics I want to now relate to you, mostly talking about performance of our application. So we now have a really good idea of the internals of Node.js and what's really happening when we make use of the Node standard library. So now we can get to leverage all this knowledge and figure out how we can start writing some really performant code inside of our applications. So quick break and we'll dive into that in the next video. Now that we've got some more basic knowledge of our event loop put together, we're going to start to look at some really interesting behavior around Node.js inside this section. In particular, we're going to take some of the code that you and I wrote in the last couple of videos, and we're going to merge it all into one mega example. And when we put this example together, you're going to see some mind-boggling behavior that really ties a lot of these topics together. And in my opinion, this might be the best Node.js interview question you will ever come across. All right, so we're going to put together a code example here. It will not behave the way you expect. And I think that it would actually be kind of a good interview question, just in my opinion. Anyways, let's get started. So we're going to take some code out of our async.js file and our threads.js file, and we're going to kind of merge it together in one example. So I'm going to make a new file inside of my main directory called multitask.js, like so. Then inside this file, I'm going to grab everything from async.js and threads.js and just copy paste it all inside of here. And then we will kind of play with the code a little bit. So we'll first go into async. I'm going to copy everything inside of here, and I'm going to paste it into multitask.js. I'm then going to do a little bit of cleanup on these requests right here. So I'm just going to delete all the do request statements. All I want to have right now is where we get our start date, the require statement at the top, and the do request function, like so. Next, I'll go into threads.js, and then over here, I'm going to get just one of those callback functions, one of the PBK df2 function calls. I'm not going to copy paste anything out of here, because if we start to copy paste multiple things, it's just going to get a little bit confusing. So I'm going to copy this one function call. I'll then go back over to multitask.js, and I'm going to create a new function called doHash. I'm going to put our hashing function call into that thing. So I'll say function doHash, like so. And then I'll paste in our PBK df2 function. And I'm also going to update the console log to say hash, like so. Okay, let's very quickly make sure that we also require in the crypto module before we forget that. So I'll go back up to the top, and I'm going to require in the crypto module, like so. All right, let's now go over to our command line. We're going to run this file, and we're just going to make sure that everything works and that we don't have any typos. Right now, we are not calling doRequest or doHash. I just want to make sure that we don't get any errors right now. That's all. So I'm going to go back over to my terminal, and I'll run node multitask.js. And when I do so, I don't see any errors. So that's exactly what I expect. Okay, so as it stands right now, this file is pretty boring, but we're going to add in one additional module to this thing, and then we're going to call a couple different functions, and that's when we're going to start to see some pretty interesting behavior. So here's the third module I'm going to require in. I'm going to say const fs is require fs. As a reminder, fs right here is the file system module. So we can use this module to read files off of our hard drive. Underneath our two function calls, or our two functions doRequest and doHash, I'm going to add in a new function call to that fs module. And we're going to use the fs module to try to read all the code that we just wrote into this multitask.js file. I know this might seem like a weird thing to do, but trust me, we're getting to a point here very quickly. And as soon as we put together this snippet of code, you'll then start to see some pretty interesting stuff. All right, so we're going to try to read everything inside of multitask.js, the file we just created. So I'll say fs.readFile. I'll put in the file name that we just created, multitask.js, like so. I'll then put in the file encoding, which is UTF-8, and then I'll add in a little callback. And inside this callback, we're going to do that same kind of benchmark thing that we've been doing all along. So inside of here, I'll add a console log. I'm going to give it a string of fs, so we know that this console log is coming from the file system module. And then we will do our date.now minus start, like so. All right, so we've now got a function doRequest, doHash, and then this last read file right here is just going to immediately be invoked as soon as we run this file. So now here's where things start to get really, really crazy, okay? Here's where things are gonna get really, really interesting. I'm gonna add in a function called to doRequest right above. So remember, doRequest is gonna make an HTTP request over to Google. And then down below, here's where things get crazy. I'm going to say doHash, so that's going to calculate our hash with a PBK df2 function, and I'm going to call it 4 times, like so. Okay, so let's now take a glance at this code and really try to figure out what's going on. So when we run this file, we're going to first try to make a request over to Google. We're then going to attempt to read all the contents of our current file, multitask.js, and then we're also going to attempt to calculate 4 hashes. Now my question to you, and this is the interview question. This is like a total brain bender. My question to you, what order are we going to see these console logs appear? We've got one console log for the request. We've got some console logs for the hash function. And then we've now got a console log for the file system module right here as well. So we're very clearly doing the HTTP request first, and then the read file, and then 4 hashes. So I want you to just sit for just a second and I want you to think about what is going to happen, okay? Try to make a guess as to what order we're going to see these console logs appear. And as soon as you have some idea, let's go back over to our terminal and we're going to run this file and see what happens. All right, here we go. So multitask.js. We're going to run this. And here's our result. Okay, so I got to ask you, is this what you expected? Right here at the very top, this is the benchmark from the HTTP module. We then see exactly one console log from that hashing function, and then we see the file system module call, and then we see the 3 remaining hashes. Let's try running it again and just see if we get the exact same behavior. And we definitely get the same. So what in the world is going on here? Reading from our hard drive with that fs module call right here, there's no way that operation takes 2 seconds when it runs. There's no way. There's no way that reading a file off of our hard drive can possibly take 2 seconds. Let's try commenting out all these do hash calls right here and just seeing how long it normally takes our read file function right here to run. So I'm going to save that. I'll run it again. And now you'll see that reading off my hard drive takes about 26 milliseconds. Extremely, extremely fast. And there's no way that normally it would take 2 seconds like you see right here. So clearly we have some super interesting behavior right here. Let's take a quick break. We're going to come back to the next video and we're going to look at a couple different diagrams to figure out exactly why we are seeing this behavior right here. So quick break and I'll see you in just a minute. In the last section, we put together a big mega example with a couple different pieces of code from several different files we've worked on before. When we ran this file, we saw some really interesting behavior. So I'm going to run it one more time over here. So in the result, we see the HTTP request come back first. We then see exactly 1 hash, then the file system callback, and then the remaining 3 hashes as well. So there's a couple elements here that seem to be very, very interesting to me. First off, why do we always see exactly 1 hash console log before the result of the file system? And then secondly, why do we always see the HTTP request complete first? Both the HTTP request right here and the file system are both asynchronous calls. It takes some amount of time for them to complete. So why do we see always the HTTP one finish almost right away or relatively right away, but then the fs module call right here always seems to be finished after the first hash? Well, in this section, we're going to take a look at a couple different diagrams and try to figure out exactly why this is occurring based on the knowledge we've now picked up on the event loop. So let's get to it. Now, this is the real crux of the issue right here. This is like the entire grounding to understand why we're seeing this behavior. Remember, in the last couple of videos when we were talking about the event loop, we had said that internally, Node makes use of a thread pool for some very specific function calls. In particular, almost everything inside of the fs module or the file system module makes use of this thread pool. And as you and I very well know, that crypto module function, pbkdf2, also makes use of the thread pool as well. However, the HTTPS module that we're using does not make use of that thread pool. And instead, it reaches out directly to the operating system and leverages the operating system to do all that networking work for us. So while the fs module makes use of the thread pool, the HTTPS module does not. So with that in mind, let's now take a look at the kind of timeline of what we just saw. So I think this right here, we'll just look at this diagram for a second. This is just kind of clarifying the time that we saw on all the console logs. So the HTTP call resolved right away, but we had to wait a really long time for all the other function calls for some reason. Let's take a look at what this read file function call right here is doing, and then maybe some of the pieces are going to come together and you're going to start to understand why we are always waiting for the read file call to take so long to complete. Okay, so this is more or less what that read file call is doing internally. You don't have to really understand exactly every step that's going on here. There's just one thing that I want to point out distinctly about what happens when we call read file. So when we first call read file, Node does not just go directly to the hard drive and immediately start reading the file. Instead, it looks at the file on the hard drive and it tries to gather some statistics about it, like how large the file is. That entire process includes one round trip to the hard drive. So we go to the hard drive, we get some statistics about the file, and then the result comes back to our program. After Node has those statistics, it now knows how large it can expect that file to be, and then it is now ready to actually go and read the file. So then Node actually goes back to the hard drive, gets the file contents, and returns them to our application. And then eventually calls our callback, and that's when we saw our console log. So the really key thing to keep in mind here is that there were two distinct pauses that occurred. We had one pause in this entire read file call where we were just waiting on the hard drive to return some statistics about this file. And then we had a second big pause as Node went back to the hard drive and started to actually read the contents out. So with this in mind, let's now look at the final diagram that really explains what was going on. Okay, so you can see we've got a couple different elements here in this diagram. On the bottom, we've got that same thread pool that we were talking about previously with its 4 default threads. Now the first thing to realize here, so this is why this is such a good interview question, is because it really makes you understand a lot of different pieces of Node. The first thing to realize is that the HTTPS module call, it's really HTTPS, that does not involve the thread pool at all. It completely skips the thread pool and makes use of the underlying operating system. So when we make that request, it doesn't care about what else is going on inside of our program. It doesn't matter. It makes the request, and as soon as we get a response back, the response is returned to our code inside the event loop, and then we see that console log appear immediately. So the HTTP request, I just kind of threw in there so that you have the reminder of, oh yeah, this happens outside the thread pool. Now the reason that the FS module call got delayed so long is specifically because of the way that the thread pool works. So the instant that we made all those function calls, like these calls right here, you can kind of imagine that it set up 5 different tasks to be executed inside of our thread pool. First, it said, okay, we need to go read the file. And then it also said, okay, also in this thread pool, we need to do 4 hashes. So once those 5 tasks all got loaded up, the first 4 each got assigned to some thread. So the file system call got assigned to thread 1, then PBK df2, the first call, went to thread 2, 2 went to 3, and 3 went to 4, and so on. Now, threads 2, 3, and 4 right here are going to immediately start churning away at these hash calls, and it's going to try to calculate those hashes as fast as they possibly can. And meanwhile, thread 1 over here is going to start working on the file system call. Now here's the really critical point. The instant that the FS module call got loaded into thread 1 started to go through this process right here. So it said, okay, let's see, I have to do everything revolved around reading some file, whatever. Well, I guess I'm going to go get some stats about that file. And then it went to go get some hard drive, or access the hard drive and get some information about that file. Now during that phase, thread 1 starts to reach out to the hard drive. And as soon as thread 1 puts that request into the hard drive, this thread right here then realizes, hey, you know what? I'm going to be waiting for quite a while. I'm going to be waiting like forever on this hard drive to get me some information back. So I think that while I'm waiting for that information, I don't care about this FS task anymore. You know what? That FS task, it can just sit around and it can wait, because I have to wait literally forever to get some information back from the hard drive. So as soon as it reaches out to the hard drive, thread number 1 then says, hey everybody, I'm available to do something else. Oh, I need to calculate some hash for PBK df2 call number 4 over here. Great, I'm going to start working on that. And so thread number 1 temporarily forgets about that file system call, and it starts calculating hash number 4 over here. Then eventually, out of thread 2, 3, and 4, one of these is going to finish. So one of these is going to finish. Maybe it's the thread 2 working on call 1 right here. So this call gets completed, and now thread 2 has now been opened up. Thread 2 finishes that first hashing function. It does the console log, which is what we saw right here. And then thread 2 says, okay, I'm now ready to pick some work back up. So thread number 2 sees that there's still the pending file system call that needs to be worked on right here. Thread number 2 then looks to see if it has gotten any information back from the hard drive, like those statistics that we were just talking about. And in this case, yes, it has. So then those statistics, I know this diagram's starting to get crazy, but you can imagine that these statistics come back into thread 2, and then thread 2 starts continuing work on the file system call. It then makes another follow-up request to the hard drive to get the actual file contents, but this time when it makes that follow-up request to actually get the file contents, like this step right here, there's no other work for it to do, so it just sits around and waits for it to come back. And then as soon as those file contents come back, then thread number 2 processes them, and we then see that console log appear. So that's why we saw over here, we always saw one hash get completed before the file system module. Because we queue up that file system call, that thread does some initial work, it makes a request over the hard drive, that thread then says, hey, you know what, the hard drive's going to take forever, I'm going to do something else. And so it picks up one of the other hash calls. It starts working on that, and then eventually another thread will finish some hashing call, and it will go back and continue working on the file system. Whew. All right, so that's it. That's what's going on behind the scenes here. Like I said, I think this would be like the most insane interview question ever because it really requires you to understand exactly what Node is doing internally. You have to understand, first off, that the HTTP module does not work with the Threadpool. You have to understand that the FS module does, along with the crypto module PBKDF2 function. And then you have to also understand that the Threadpool by default has 4 threads available to it. Now, just one quick thing I want to throw in here as kind of a follow-up tricky question, maybe not that tricky. If we went and increased the Threadpool size inside of multitask.js, remember we can do that at the very top by setting this environment variable. So if we increased our Threadpool size up to 5 and then ran this file again, what do you think would happen? Well, I bet you could take a pretty good guess here. So when I run this, now we have an extra thread that can be 100% responsible for everything that the file system call needs. And so that 5th thread is now entirely dedicated to working with the hard drive and doing whatever needs to occur. And that's why now we see the result right here appear immediately. And then likewise, if we go all the way down to 1, so only 1 thread now, this 1 thread is going to do some initial work on the file system call. It's then going to say, okay, file system, we're waiting on the hard drive, I'll catch you later. It will then process all 4 hashes, and then eventually once those are all done, it will then resolve or do the rest of the work for the file system call. So if we now do this, we'll see hash 1, 2, 3, 4, and then the result of the file system call. And all the while, the actual HTTP request is completely unchanged because it's not touching the Threadpool at all. All right, like I said, I was super excited about this because we finally got through all the event loop stuff, and now you can start to really understand this crazy behavior that you start to see in Node. So this has been a lot of fun. Let's continue in the next section, and we're going to start looking at some performance of Node. So quick break, and I'll see you in just a minute. In the last section, we spoke about some big concerns we have around performance whenever we are doing a lot of work inside of our event loop. In this video, we're going to start to look at some different strategies we can use when that is unavoidable to do. So sometimes you just have to do a lot of work inside of your event loop, and there's really no getting around it. So we're going to look at 2 different ways that we can at least somewhat mitigate the performance impact that this has on our application. In particular, we're going to look at how we can set up Node to run inside of cluster mode. Cluster mode is used to start up multiple copies of Node that are all running your server inside them. We cannot somehow trick Node into running with multiple threads, but by starting up multiple copies, we get multiple instances of the event loop. So it vaguely somewhat works in a similar fashion as making Node kind of multi-threaded. The other thing that we're going to investigate is using worker threads to do a lot of performance work inside of our app as well. These worker threads are going to use the Threadpool that is set up by Libuv whenever we start up our Node application. Now, one thing I want to tell you right now, and I want to make this really clear, starting up Node in cluster mode to handle a lot of heavy-duty performance relevant calculations or whatever it might be that you're doing, the recommended approach here for improving performance of your application. This is a very well battle-tested procedure, and it's something that we are very confident will work correctly and definitely enhance performance inside your application. Using worker threads, which I'm also going to show you in this course, is something that is way more experimental. And it's something that I'm showing you just for the sake of your knowledge and your own curiosity. So if you want to apply these techniques to enhance the performance of your application, I definitely encourage you to look at cluster mode first, and then maybe at some point in the future when we feel much more comfortable with threads and worker threads, then check this approach out. Okay, so just be aware of that. So let's take a quick pause right now. In the next video, we're going to start working on a tiny little server that we're going to use to eventually implement clustering and worker threads. So quick break, and I'll see you in a second. In the last section, we started talking about improving the performance of node applications by using clustering mode or worker threads. Before we dive too deeply into either of these topics, however, we're going to set up a tiny little Express application. And we're going to use this Express app to demonstrate both these techniques right here. So let's set up the app first, and then we'll apply both these techniques to that app. I'm going to get started first by going back over to my code editor. I'm in the same directory I was in before, so I'm just going to let all these files kind of commingle. And inside this directory, I'm going to make a new file called index.js. So this is where we're going to write some code for our tiny Express server that we're going to work around with in just a little bit. I'm going to first get started by requiring in Express. So I'll say const express is require Express. I'll then generate a new app out of that. And then I'm going to set up exactly one route on this application. So app.get /, and whenever someone tries to go there, I'll take the request and response, and I'm going to send back just the string hi there, like so. And then finally at the bottom, I'll say app.listen, and we'll listen on port 3000. Doesn't really matter. Any port's fine. Now notice that we are requiring an Express, so we do have to install this as an npm module inside of our project directory here. So to install that as a dependency, we have to first generate a package.json file, and then we could use npm install to install Express. So to generate the package.json file, I'm going to open up my terminal. I'm going to make sure I'm in that same directory, and I'll run npm init. And then of course we get asked these boring questions, whatever. We'll just hit enter to get through them. And then finally we can run npm install save Express, like so. Now this is going to take just a moment, so I'm going to let the installation finish, and then I'm going to start the server up with node index.js, like so. Okay, very quickly, let's flip on over to the browser and just make sure this thing is working. So I'm going to open up a new browser window at localhost 3000, and it looks like, yep, everything appears to be working. So I see the text, hi there, appear on the screen. Cool. Now we are going to be making some frequent changes to that index.js file. And normally I would tell you, let's install a automatic code reloader like nodemon or something like that to keep us from having to constantly close this process and start the server back up. However, nodemon by default out of the box does not work very nicely with clustering. So for this exercise, I'm going to ask you, do not use nodemon here. I know it's a pain to have to restart the server all the time with every code change we make, but we are going to do that by hand. So please do not use nodemon here if you usually do use it. As a quick reminder, you can restart the server very easily by hitting Control-C. That kills the server, and then you could press up arrow to get the same command back and hit enter. So hey, it's not the worst thing in the world. Okay, so we've now got our tiny Express application put together. Let's continue in the next video where we're going to start talking about applying clustering to this tiny snippet of code. So quick break, and I'll see you in a minute. In the last section, we started putting together our Express application. We're going to use that thing to test out both cluster mode and worker threads to enhance the performance of our application. So let's first get started by doing a quick overview around cluster and clustering inside of our app, and then we're going to actually implement it inside of our Express application. So let's get to it. All right. So the first thing to keep in mind here, and this is all super relevant because we just spoke about all that event loop stuff, is that whenever some request comes into our server, it gets processed inside of one single thread that contains our event loop. So some request comes in, our server processes it, and then it generates a response. Now in general, this totally works out just fine for us. And certainly in the vast majority of Node applications, if you follow this pattern right here, you're going to have a great time and things are going to work out just the way you expect. However, we start to run into some really big issues when these incoming requests right here take some amount of time to process. So if we have some request coming in that requires a lot of processing power, like a lot of JavaScript code that you and I write that takes a long time to run through, then our Node server is not going to be able to process incoming requests as effectively as it otherwise would. Now I'm using a lot of kind of like, whatever words here. Might seem a little bit boring, so I'll tell you what. Let me show you a quick example of exactly what I'm talking about. I'm going to go back over to my Express server right here, and right above my request handler, I'm going to create a new function, and I'm going to call this thing do work, like so. Whenever we call do work, we're going to pass in an argument called duration. Now the sole purpose of this little function right here is to try to use as much CPU processing power as it possibly can for some set duration. And this duration will be some number of milliseconds. Now there's a very, maybe I shouldn't say clever way of doing this, but there's a very easy way that we can kind of simulate doing a lot of work for some very specific set duration. So I'm going to say const start is date.now. And then I'm going to write out a while loop. I'll say while date.now minus start is less than duration, and then I'll open up the while loop like so. So the instant we call do work, we take the current time. We then enter the while loop right here, and then check the condition. So if date.now, if like the new present time minus the starting time is less than duration, then we're going to continue running this while loop right here. So in total, this function is going to try to execute this while loop as fast as it possibly can for some set duration in milliseconds. And it's going to do absolutely nothing else. So let's now add a call to do work inside of our request handler and just see what type of impact it has on our application. So right above our res.send, I'm going to add in do work, and I'm going to say try to do work for 5 seconds straight. So 5,000 milliseconds, which is 5 seconds. Now here's the critical thing to keep in mind. This code right here is going to be executed inside of our event loop. This doesn't get thrown out to an event pool. It doesn't get handled by the operating system or anything like that. This is some code that is going to be processed in our event loop. And for these 5 seconds, while we are running this while loop, our event loop can do absolutely nothing else. That means it cannot handle other requests. It can't do other like database queries or write files, whatever else, or anything else while this while loop right here is running. So let's see that in action right now. If I go back over to my browser, I'll refresh the application and notice how, I just forgot, we got to restart the server very quickly back at the terminal. I'm going to restart my server very quickly. I know I just said that we're not doing nodemon, but I already forgot about that. So I'll restart the server, and then if I go back to my application with my request log up here, I should be able to refresh the page, and then you'll notice that we're just going to sit around for 5 seconds and wait for this thing to load. And then eventually there, all right, 5 seconds just about. Now, okay, well for this one request, who cares if it takes a little bit longer? But remember, we are blocking the entire event loop with that one little do work function call. And that means that our entire server can do absolutely nothing else while that is being processed. So let me show you the effect of that. I'm going to open up a second tab inside my browser, and I'm going to enter in localhost 3000, but I'm not going to go there just yet. So let me tell you what I'm going to do. I'm going to hit enter right here. That's going to start up my server running that do work function for 5 seconds. Then inside of this second browser window that I have right here, I'm going to very quickly come back over and I'll hit refresh right here. And you're going to see that it's going to take even longer than the 5 seconds we see right here, because our server is going to be busy processing this request, and it will not even start considering our second one over here until the first one is complete. So let's try this out very quickly. I'm going to hit enter. I'm going to flip back over as fast as I can and hit refresh. And now we're going to wait. Okay, and you know what? It took 5 seconds. That's really frustrating, but basically it's just because the way that this page over here loaded up. Watch this. I'm going to do it one more time. In the second tab, I'll hit reload. I'll come back over and hit reload. And now you're going to see exactly what I'm talking about. I know that first time was a little letdown. Okay, so we're waiting. And this time it took about 8.5 seconds. That missing 1.5, like 10 seconds minus 8.5 right here, so that 1.5 seconds just about, was essentially the time that it took me to flip between these two browser tabs and hit the refresh button over here. So as you can see, this is kind of a long demonstration, but you can very plainly see that as soon as you and I start writing some JavaScript code that takes some amount of time to execute, our entire server is blocking any other requests that are coming in. And it can do absolutely nothing else until that original request gets resolved and handled. So clearly the effect of some very long running or computationally intensive code inside of a Node project can be quite catastrophic. Definitely not ideal at all. All right, so with that in mind, now that we understand why having Node run into a single thread right here can sometimes be not a very good approach, let's come back in the next section and we're going to start to see how clustering can start to maybe not solve this problem, but at least mitigate it. So quick break, and I'll see you in just a minute. In the last section, we saw a very practical example where having a single thread to run our Node server, it definitely had some harmful consequences on our ability to service incoming requests. In this section, we're going to continue and start talking about clustering and how it's going to solve this issue. All right, so here's our first diagram of what clustering kind of looks like behind the scenes. When we start to use clustering inside of a Node application, we're going to be starting up multiple Node processes. There's always going to be one parent process or one kind of like overarching process called the cluster manager. The cluster manager is responsible for monitoring the health of individual instances of our application that we're going to launch at the same time on our computer. So all the stuff that we see right here, these are all instances of our application that are running on our singular computer. These are not being spread out to multiple machines or anything like that. It's multiple instances, one computer. The cluster manager itself doesn't actually execute any application code. So in other words, the cluster manager isn't really responsible for handling incoming requests or fetching data from the database or doing anything like that. Instead, the cluster manager is responsible for monitoring the health of each of these individual instances. So the cluster manager can start instances, it can stop them, it can restart them, it can send them data, it can do other kind of like administrative tasks, essentially. But it's still going to be up to these individual instances of our server to actually process incoming requests and do things like, say, access the database, or handle authentication, or serve up static files, or whatever else we might usually use our Node application for. Now, understanding how all this clustering stuff works can be a little bit challenging just by diagrams. So I'm going to show you two quick, very brief diagrams, and then we're going to flip back over to our code editor and start implementing clustering on our Tiny Express application. So these diagrams are just going to give you a taste of what we're going to do. Again, kind of expressing clustering with diagrams can be just a little bit challenging. So let's take a look. Okay, so diagram number 1 right here. This is what happens when you and I usually run a Node application from the terminal. So this is not clustering right here, just to be clear. This is what usually happens when we start up our application. You and I run a command at the terminal, like node index.js. Node takes the contents of that file, it executes it, it then starts up the event loop. So we get a single Node instance out of that entire process. And it's a very linear process. We run the command, Node looks at the file, starts up our instance of our application, and that's pretty much it. When we start to use clustering, this entire flow right here changes just a little bit. Okay, so let's see what happens. Let me take out this one right here really quickly. There we go, that's better. Okay, so when we start to use clustering, we're still going to run something like node index.js at the command line. Node is still going to boot up our application by reading the contents of that file and launching a Node instance. But here's where things get different. The first instance of Node that gets launched when we run that command is what we refer to as the cluster manager. And this is the same cluster manager that we saw in that diagram just 1 second ago. So when we run this command, we get one copy of Node, and boom, that is our cluster manager automatically created for us. The cluster manager is then responsible for starting up worker instances. And those worker instances, like what you see right here, are what are actually responsible for processing those incoming requests. To create these worker instances, the cluster manager is going to require in the cluster module from the Node standard library. So the cluster module is a standard library module, just like FS or HTTP or crypto or any of those other ones. There's one particular function on that cluster module called fork. And whenever we call that fork function from within the cluster manager, something very interesting happens. So when you and I call fork, Node internally goes back to our index.js file and it executes it a second time. But it executes it that second time in a slightly different mode. And we're going to see exactly what's different about it. But when it executes that file a second time, that then starts up our worker instance. So in other words, you can basically imagine that our index.js file is going to be getting executed multiple times by Node. The very first time, it's going to produce our cluster manager, and then every time after that, it's going to be producing our worker instances. So that's clustering with two very brief diagrams. Let's pause right here. We're going to come back to the next video, and we're going to start to actually implement all this clustering stuff in our index.js file. So quick break, and I'll see you in just a minute. In the last section, we went through two very quick diagrams just to give you a taste of how clustering works. We're now going to flip back over to our index.js file and implement clustering inside of our Tiny Express application. All right, so back over here. We're going to first get started off by requiring in the cluster module at the very top of the file. Again, remember, this is one of the Node standard library modules, just the same as FS or crypto or any of those other ones. So I'm going to say const cluster is require cluster. The library right here has a couple of different properties and functions assigned to it that are going to be absolutely indispensable for us to set up our clustering process here. The first thing I want to do, just to show you the first property and possibly one of the most important ones that we're going to need to get access to, is a property called isMaster. So I'm going to add a console log right here. I'm going to say cluster.isMaster. I'm then going to save this file, and then I'm going to go restart my server inside the terminal and see what the result of this console log is. All right, so here is my running server. I'm going to kill it with Control-C, and I'll start the server back up with node index.js. And when I do, you'll immediately see that I get a console log result of true right here. So remember how we said just a second ago that when we first execute node.js, Node executes the contents of that file and then starts up a copy of Node that we refer to as the cluster manager. The cluster manager has that isManager property always set to true. As soon as we start forking off additional worker instances, however, that isManager flag is going to be set to false. So for cluster manager right here, we have isManager set to true. For all the worker instances, we have isManager set to false. And we basically use that single property, this single property right here, to decide what the file, what this index.js file should do whenever it gets executed. Because remember, as soon as we start doing the fork, Node is going to execute that index.js file a second or third or fourth time. So when we run this file, we need to make sure that we behave slightly differently depending upon whether we are running in the cluster manager or a worker instance. So to give you a very practical example of how we're going to do that, we're going to remove the console log right here, and we're going to replace it with a little bit different code. So I'm going to say if cluster.isMaster, and I'm going to open up an if statement, and then I'm also going to add on an else statement. So here's my opening curly brace right here, and I'm going to put all of my server related code into this else case. So I'm going to highlight all this stuff right here. I'm going to indent it in, and then I'm going to close off that else statement with a curly brace at the very bottom, like so. And then I'll save the file. Now at present, whenever we run this index.js file, we don't have a case for what to do if we are currently executing this file in the master mode. So I'm going to add in one little instruction to this thing. I'm going to say cluster.fork, like so. Okay, so let's take a pause right here for just a second, and I don't mean like a break. I want to add in just a comment or two to this file to very clearly describe what is happening when we execute this file with node index.js at the command line. So the very first time that we execute this file at the command line, we're going to ask the question, is the file being executed in master mode? And if it is, then we're going to enter this if statement right here, and we're going to call cluster.fork. That's going to cause index.js to be executed again, but in slave mode. And rather than slave mode, a better term here might be like child mode, like so. If the file is being executed not in master mode, so if we are a child, then we're not going to try to fork anything, and instead we're going to enter the else case. So in that else case, I'm going to add a comment that says, I'm a child, I'm going to act like a server and do nothing else. So that's pretty much it. Now every time we call cluster.fork, isMaster will be set to false, so we enter the else case right here, and all of our child instances behave like a normal Express server. Now before we move on, let's flip over to our terminal very quickly. I want to restart our server and test it out and just make sure that everything is still working the way we expect. So I'm going to go back over to my terminal. I'm going to kill the running server. I'm going to start it back up with node index.js. And I should be able to go back over to localhost 3000, refresh the page, and then after a 5-second wait, because remember we still have that pause in there, I should see the page refresh again. Very good. Okay, so we set up a cluster, but as far as I can tell, it's not really doing a whole lot for us. So let's come back to the next video, and we're going to start to massage the code in here just a little bit to make it much more useful than it is right now. So I'll see you in just a minute. In the last section, we added some code to our index.js file to automatically start up one child anytime we start our server from the command line. When we start up just one child, that's not really doing a whole lot for us. When we have one child, that's basically doing the same thing as just executing our server in normal mode. Because when we have only one child, we still only have one instance of the event loop, and we're not really gaining any performance benefit or anything like that. We can easily start up additional children by simply calling cluster.fork additional times. So if we want to start up, say, 2 or 3 additional children, I can call cluster.fork, 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 like so. I've got 4 calls to cluster.fork. That means that in addition to the first time of executing the index.js file, it will be executed an additional 4 times. And each time, isMaster will be set to false, so we will set up all the Express logic that you see right here. Now I want to show you a very practical example of what happens when we start to set up these additional instances. Right now we've got this root route that always has a pause of 5 seconds, as you see right here. I'm going to set up an additional route inside of here. I'm going to say app.get/fast. And then inside this route handler, I'm going to do a res.send, and I'll send back the text, this was fast, like so. So now anytime that we try to get that root route, we're going to have a pause of 5 seconds. And anytime that we try to get the route of /fast, the page will load up, hopefully just about instantly. Remember that at present, we have multiple copies of our server running. Let's try testing out the application as it is right now, and then we're going to come back and remove some of these additional children, and we'll see how quickly we can load up all these different routes that we see. Okay, so let's first remember to restart our server. Okay, that's good. I'll now go back over to my browser. Inside of a second browser window, I'm going to try to navigate to localhost 3000/fast. I'm going to first go back to the first window. I'm going to start to refresh this page, and then I'm going to flip over to that second one, and I'm going to try to load up that second page as fast as I can. So we are now going to make 2 separate requests, essentially in parallel, essentially at the same time. Okay, here we go. I'm going to hit 1, 2, 3, refresh. I'll go over and hit enter. And now you notice that over here, I see this was fast, but over here, it still took 5 seconds to load up this page. Now maybe you're thinking, okay, whatever, how is this an improvement at all? Well, remember what happened when we first tried to load up 2 instances of this hi there page with that 5-second delay. when we only had that single instance of the server, we had to wait for that first request to be completed. We had to wait that full 5 seconds before the second 5-second request would even start. So what we just saw was loading 2 separate requests at the same time, and they both went very quickly, or at least I should say the second one went very quickly, because we had 2 separate servers handling each request. Let's now go back over to our index.js file. I'm going to comment out all these additional children that we created, and I'm going to leave it with just 1 child. And then we're going to repeat that same process again. So I'm going to save the file. I'm going to close the running terminal and restart the server. And then I'll go back over to my browser. So this time I'm going to refresh this page, and then very quickly I will tab over here and try to refresh the fast route. And we're going to see that it takes the fast route quite a bit of time to actually load up. And just to prove it, I'll open up my request log over here so we can actually see the amount of time that it takes. Okay, here we go. 1, 2, 3. I'll refresh. And now we're just sitting here waiting until finally after about 4 seconds, because that's how long it, like the 0.7 second difference here is essentially how long it took me to tab over. So now this time around, we only had the 1 server to handle both of these requests. The first request over here took a super long time to complete. It took that first full 5 seconds. And during that time, our server could do absolutely nothing else, even though we had that incoming request. So this is a very practical example of where clustering can play a huge benefit inside of your application. If you have some routes inside of your app that usually take a while to process, but you have other routes that are very quick, then by using clustering, you can start up multiple instances of your server that more evenly address all the incoming requests that are coming into your application and have some more predictable response times. Now, it definitely sounds like clustering is the best thing in the world, but there definitely are some corner cases to be aware of. So let's pause right here. We're going to come back to the next video, and I'm going to show you 1 or 2 cases where, well, maybe clustering is a benefit, but it's not quite as much as a benefit as you might be thinking. So quick break, and I'll see you in just a minute. At this point, you're probably thinking that all this clustering stuff is awesome and that you can get some real performance benefits inside of your application with doing just a tiny bit of work. You also might be thinking that, gee, seems like it's really great to just use more additional children. So maybe inside of my application, I'm going to just start up a whole bunch of different forks like so, and that means my application is going to run really fast. Well, unfortunately, life is not quite so simple. There's definitely a point of diminishing returns when you start using clustering. So in this section, and the next 1 or 2, I'm going to show you some situations in which adding a whole bunch of additional children really has diminishing returns, and in some cases can actually be kind of catastrophic for your application. Before we start making any changes to our code base, I think that you can agree with me that we probably need a more scientific way of measuring how long it takes our server to process requests. In the last couple of videos, I've been going to localhost 3000 inside my browser and then refreshing the page as fast as I could. And that's definitely not very scientific. So let's first take a look at a little program that we're going to use to benchmark the performance of our server. And then we're going to come back and play around with the code inside of here a little bit. And I'm going to show you where clustering doesn't work out quite so well. All right, so I'm over at my terminal. I'm going to open up a second terminal window, still inside the same directory. Okay, so here's my second window. I'm still inside of my project directory. Now, I want you to know right now that the little program we're going to use to do this benchmarking is only installed by default on Mac OS and some Linux distributions. So if you are on Windows, the command that I'm going to use right here is not going to quite work out. And if it was easy to install this program on Windows, I would show you how to do it. But unfortunately, it's just kind of challenging on Windows. So if you're on a Windows machine, hey, don't sweat it. I encourage you to just follow along and watch these benchmarks. Honestly, it's probably just a lot easier if you kind of pay attention to what I'm doing rather than trying to replicate it on your machine, because there's kind of a few different variables at play here in how the exact numbers around all this clustering stuff is going to work out. So in other words, if you're on Mac OS, you can follow along with these commands, but if you're on Windows, I encourage you to just watch for a little bit. Okay, so here's the program we're going to use to benchmark our machine. The program is called Apache Benchmark, or AB for short. So you can put in simply AB, again, if you're on Mac OS, run it, and it will show you a bunch of help. You can read all this help stuff right here. Otherwise, obviously, I'll show you how to use it as well. So to use AB, we can specify a number of requests to make to some specific server. Apache Benchmark will then make all those requests, and then it will print out some statistics about how long it took for those requests to be processed. So let me give you a very quick example. Remember that back on our server right now, we have that /fast route. Let's try benchmarking how long it takes to run that route right there. So to do so, I can call AB-C, and we'll do how about like 50-N 500, and then localhost :3000/fast. So you can read this right here as use Apache Benchmark to make requests to localhost 3000/fast. Make a total, so -N right here means total number, so make a total of 500 requests. And the -C of 50 means use a concurrency of 50. That means try to make 50 requests at the same time. Now, of course, these requests might finish at different times, so it's not going to do it in batches of 50. Instead, it's going to try to make sure there are always 50 requests running at any given point in time. So try to make 500 requests and make sure there are always at least 50 requests pending. So I'm going to run this and we'll just see what happens. Okay, so as you can see, we get quite a good amount of output here. Now, usually there's a couple of different numbers that we like to look at. I personally like to see requests per second. So this is how many requests per second our server processed. I like to see the amount of time that it took on average per request. And I also like to see how many, or kind of like what distribution for time of the like buckets of the requests made. And it's kind of like more of a histogram. Maybe not a histogram. Is it a histogram? I don't know. Someone who's really good with graphs can tell me if this is a histogram. Basically, this is saying that 50% of all requests were served or responded to within 70 milliseconds. But then one request at least took 130 milliseconds to respond to. Definitely kind of on the slow side. Okay, so now we have a much more scientific way of benchmarking the performance of our server. Now that we have this in place, let's come back in the next section and we're going to make some modifications to our server, and I'm going to show you exactly where clustering does not quite work out so well. So quick break, and we'll look into that in the next video. In the last section, we got a better idea of how to get some concrete results around the performance of our application. We're now going to start to refactor our index.js file here just a little bit, and then start to benchmark it to get a better idea of when clustering starts to not quite pay off so much. The refactor we're about to do is going to be just a little bit long, so we're going to try to get through it as quickly as possible, and then we will immediately start benchmarking our app in the next video. Okay, so let's get to it. So what we're going to do for the most part here is replace the doWork function. The doWork function definitely is good at simulating a big pause or some blocking code inside of our application, but it doesn't really do a good job of simulating true, actual work, like some computation, some fixed set of data that we have to chomp through. The doWork function always tries to pause for the exact same duration, and that doesn't really give you a very good sense of what's going on when it starts to come to clustering. So we're going to replace the doWork function with a different function that better simulates doing some real computation on our server. So I'm going to delete the entire doWork function, and then I'm also going to clean up the doWork function call from inside the root route as well. Now instead, we're going to reuse one of the same functions we used previously in this course. To simulate some amount of work inside of our cluster, we're going to use that pbk df2 hashing function. Now I don't want to rewrite that entire function out because I'm so lazy. So I'm going to open up my threads.js file, and I'm going to copy paste one of those function calls over to my server. So I'm going to get this one call right here. I'm going to go back over to my index.js file, and I'm going to dump it right into my root route request handler. I'm then going to take out the console log, and then to really simulate some amount of work that has to be completed before our server will respond to this request, I'm going to take that res.send and I'm going to put it into the callback like so. So this now means that anytime someone makes a request to our root route, we're going to calculate the hash, which for me on my computer takes just about 1 second, as we saw very many videos ago. And then after that 1 second of work, we're then going to send a response back to whoever made the request. The other thing I'm going to do very quickly is just make sure that I require in the crypto module before I forget. Now I'm going to make one other change here, and this change is going to seem a little bit arbitrary, but it's going to make understanding the benchmark results that we get much easier. Okay, so this is, again, it's going to be a little bit of an arbitrary change, but it's going to make understanding our benchmarks so much easier to comprehend. So I'm going to say that all of the children inside of our cluster will only have one thread available in their thread pool. Okay, so just one thread in the thread pool. To be clear, whenever we create a cluster, every single child has their own separate thread pool. So normally every child that we would create has a group of 4 threads that they can use for computation. But just to make these results a little bit easier, I'm going to restrict it to 1. And recall we can do that by placing a line at the top of our index.js file of process env uv underscore threadpool underscore size, and I'm going to set that equal to 1. This does not restrict the total number of threads in our entire cluster. It means that every child in the cluster only has 1 thread available. And again, for like the 3rd or 4th time, this is just to make understanding our benchmark results a lot more straightforward. Okay, so let's pause right here. We're going to come back in the next video, and we're going to start to do some more benchmarking, and we're going to see where clustering doesn't quite pay off so well. So quick break, and I'll see you in just a minute. In the last section, we finished up a little refactor of our application. We now have exactly 1 child in our cluster. Make sure you've only got one cluster.fork right here. And that 1 child has just 1 thread available to it. We're now going to start running some benchmarks on our application, and I'm going to show you where you start to get diminishing returns by increasing the number of children inside of your app. So let's get to it. I'm going to flip back over to my terminal, and I'm going to make sure that I restart my server by running node index.js. And then I'm going to open up my second terminal window where we're going to do a little bit of benchmarking with that AB command. So over here, I'm going to first start off by giving us kind of a baseline. We're going to say that when we have 1 child with 1 thread, how long does it take to process exactly 1 incoming request? So I'm going to say AB-C1-N1. So that means make 1 request with a concurrency of 1. Let's just establish a baseline here. And I'll say localhost 3000 /. We're not using fast here because remember the root route is what is actually triggering the hashing function call. The other thing I want to mention very quickly here is make sure you get on this / at the very end. For me personally, Apache benchmark breaks if I do not include that /. So I encourage you to add it as well. Okay, so let's run this and see how long it takes to run exactly 1 hashing function call. Okay, so it runs, and I see about, 1 second, very similar to what we had seen previously when we did some very manual benchmarking of our application. So I'm now going to change what's going on here a little bit. I'm going to make a very subtle change, okay? It's going to be very, very subtle. And it's going to be kind of challenging to understand the results exactly, but we'll walk through it together very carefully and you'll get a really good idea of what's going on. I'm not going to change the concurrency. Actually, let me clean this up so you can see everything. I'm going to change the concurrency to be 2, and I'm going to change the request count to be 2 as well. So now we are making 2 requests at the exact same time to our 1 child inside of our cluster. And that 1 child has exactly 1 thread available. So let's run this and now see what happens. Okay, we're waiting, and then we get some results back. So now, in this case, we get some results that are kind of challenging to interpret at the very start. Okay, let me walk you through this. You'll notice that it looks like the vast majority of our 2 requests, it says, basically all these right here, took about 2.1 seconds to be processed. But if you look very carefully, you'll see that we have a minimum request time of 1 second. So out of those 2 requests, 1 request took 1 second to complete, the other took 2 seconds. So let's take a look at a diagram that's going to help explain the result that we're seeing right here. And then we're going to be able to extrapolate this to some of the larger cluster sizes and see where our performance starts to drop off. Okay, so this is what we just ran a second ago. So this is what's happening. We have 2 requests coming into our server to run that pbk-df2 function. Now the instant that the first request comes in, and remember they're being issued at the same time, but essentially one of those is going to reach our server before the other, that very first request immediately gets picked up by the Threadpool, and our server starts to process it. As soon as that first pbk-df2 function is complete, our server responds at about the 1 second mark. And that explains the minimum response time right here of just about 1 second. Now at the same exact time, that second request comes in as well. The way I've put together this diagram is a little bit misleading right here. So technically, the second request comes in like at time equals 0 as well. But this diagram that I'm showing you is meant to give you an idea of when the actual processing in the Threadpool occurred on the second pbk-df2. So we finished up the first hash call at 1 second, and the instant that one was complete, our server then started to work on the second hashing function. That took an additional 1 second, and so it eventually sent back the result at 2 seconds. And that explains the like 2.1 second that we see right here. So the first call took about 1 second, the second call took 2 seconds. And yes, they occurred at exactly the same time, but our server only has the ability to process one hashing function at a time because we restricted that thread pool size to exactly 1 thread. Okay, so at this point, you're probably thinking, Steven, where are you going with this? I understand it, whatever, like get to the point. Okay, just bear with me. This is like gonna come together very, very nicely, all right? Just a little bit longer, let's get to it. So we're now going to look at a second condition here. We're gonna try running clustering with 2 children and see what type of response time we get now. So back inside my index.js file, I'm gonna copy paste down cluster.fork. I'm then going to go restart my server. So I'm going to kill my server and start it back up. And then I'm going to run my benchmark one more time with the exact same parameters. So 2 requests, both at the same time. In this case, we have 2 children running. So I'm going to run, and then I get the result back, and it only took about 1 second to process both those. So I have a minimum of 1161 and a maximum of like 1171. So definitely these 2 requests very clearly have been processed just about in parallel. They both came in. Clearly one child inside of our cluster picked up the first call and started processing it. And then the second child inside of our cluster started processing the second one. They both completed at the 1 second mark. We sent back the response and everyone was happy. So by using clustering, we very clearly, like no 2 ways about it, by using clustering, we have gotten a very distinct benefit here. Before, it took 2 seconds to do this work, and now by using clustering, it took us 1 second. We cut the time in half, and we should be really happy, right? So you might be thinking, hey man, this is great. Let's just keep increasing the number of children. Let's fork this process a whole bunch. I'm going to take it all the way out to 6. So I've now got 3 here, 3 here. Whenever we start up our application now, we're going to get 6 separate instances. And these 6 separate instances can all be used to process incoming requests, and everyone is going to be served a response back even faster than before. Or at least that's what you might think. Okay, that's not what's really going to happen here. So let's save this file. We're going to restart our server, and you're going to very quickly start to see where this performance benefit that you might think that you get by adding in additional children starts to fall by the wayside. So I'm going to save this file. I'm going to kill my server, and then we're going to do this process again. Now, in this case, obviously we have to increase the number of requests that are being issued here. I know that when we increase the number, you're going to say, Steven, of course it's taking longer. We're adding in more requests. Well, just bear with me. You're going to see exactly what's going on here in just a second, okay? We will make all the numbers entirely line out. So if you're thinking, Steven, you're increasing the numbers, you're crazy, of course it's going to take longer. Don't worry, I'm going to have a very solid answer for you on what's going on. So now this time we have 6 children. So I'm going to issue 6 requests all at the same exact time. Let's run this and we're going to see what happens in this case. Okay, I'm going to run it. Oh, I think I did not restart my server or something. Yeah, I did not restart the server. Sorry. Let's try it again. There we go. And now we're going to wait. Okay. well, what's going on here? How do we interpret this? So take a look. This time around, it took us 3.5 seconds like across the board. So here's my minimum of 3.4, and I've got a maximum of 3.5. So for those 6 requests, just about every single one of them took 3.5. Oops, don't want to show you that yet. Oh, I wanted to do this one over here, sorry. When we start to get the 6 in there, every single one took all the way out to 3.5 seconds. So we're kind of in this situation right here. So let's update this to be now 6, and this was 3.5, like so. So how do we explain this? Well, remember, and this is where, depending on your personal machine, like your laptop or your desktop, you're going to see slightly different results. I want you to remember that my computer that I'm recording this on right now is a dual core machine. That means that there is an absolute upper limit to my computer's ability to process incoming requests and do some amount of work. And that's not just my machine, right? That's every computer in the whole world. Every computer has some upper limit to the amount of bits and data that it can just crunch at any given point in time. So when we run our code like so, and we do 6 at the same time, that means that in those 6 separate threads that are running in my 6 separate children, we are bouncing between every hash function call at the exact same time. And our CPU is trying to do a little bit of work on this one, and a little bit of work on this one, and this one, and this one, and this one, and this one, all at the exact same time. The result is that we did not get our code executed 6 times faster or anything like that. The result is that it took significantly longer. It took 3.5 seconds to eventually get a response to everyone, excuse me. So although we were able to address all these incoming requests at the same time, the net result was that our overall performance suffered because our CPU was trying to bounce around and process all these different incoming requests at exactly the same time. So this is a very clear case where we have kind of over-allocated instances inside of our cluster. And even though we can definitely start processing all these hashes at the exact same time, which might be good, right? You know, we can start processing everything at the same time and everyone gets a response as fast as possible. The result is that we've kind of created like this big average bottleneck of mediocrity where we can only do so much at any given time, and we've been trying to do too much, so it's slowed down the overall result. So clearly there's an upper bound to the number of children that we might want to create inside of our cluster whenever we have some computationally intensive work to do inside of our application. So let me show you a solution that will work very well here. Now, maybe I'm going to take that back. I'm not going to say it's going to work very well, but I think that you'll agree with me that at the end of the day, it's probably a net benefit. So let me show you what I'm going to do. I'm going to go back over to my application. Here's my index.js file. And rather than going totally overboard with my number of forks here, I'm going to go down to just 2 like we had before. So fewer forks, you know, hey, does that mean we're going to run our server more slowly, or what's that really doing for us? Well, let's restart our server and do the benchmark and see what happens. Okay, so I'm going to restart the server. And then I'm going to run the benchmark one more time. Now notice this time I am in fact doing 6 by 6. So like I said before, if you're thinking, Steven, you're doing 6, of course it's going to take longer. This time we're back to just 2 children and I'm doing 6 on both. So let's now give this a shot and see what happens. Okay, feels like we're still waiting for a while. But when we get the result back, you'll notice that we went all the way down to about 3.4 seconds for the longest request. So the longest request was 3.4. But if you really break down what's happening here, you'll notice that our fastest requests were processed in just 1 second. So let's take what we just did and put it into a diagram to give you a better idea. Okay, so here's our new timing. So in this case, we are using clustering and we have just 2 children. But with 2 children, we know that we can only process at best 2 hashes at any given time. Now we are still kind of subject to an overload here, but let's just kind of look at the diagram and see what really happens. Now the diagram itself, just like it was before, it's kind of misleading. All 6 requests technically come in at exactly the same time, right? They all come into our server at exactly time of 0 seconds. But the purpose of this diagram is to show you when the server actually processes at each pbkdf2 function call. So the bars here represent when the CPU is actually working on each hash. So the instant that these first two function calls come in, the first two calls immediately get redirected over to the CPU. I have a dual core CPU, so each hash is executed on one CPU and gets the absolute full dedicated attention of that one CPU. So the first two take from time 0 to 1 second. And after that 1 second, I have already finished the first two hashes. Then my two running children inside of my cluster say, hey, all right, we've cleared those out. We're ready for the next two. It goes and grabs the next two, processes them both in 1 second, and then obviously does the same thing for a third time around. Now, I got a result just a second ago of 3.4. Again, that's because I'm running this video recording software, which kind of exaggerates my results right here. But in the real world, if this was like just me on my laptop with nothing else running, you would have seen 5 and 6 down here run at 3 seconds as well. So even though we have used fewer children, we actually have ended up with arguably a far better performance profile than we did previously. Not only are we finishing all of our hashes more quickly, right? We're doing everything faster than 3.5 seconds, but a bulk of those hashes are being finished significantly faster. So by increasing the number of children that you have inside of your application dramatically beyond the number of actual logical cores that you have or physical CPU cores that you have in your computer, you're going to have a net negative effect on the performance of your system. So the end result of all this, after gabbing away about all this for a super long time on my part, I apologize, but the net result is, what I'm trying to say here is, yes, clustering is great, but you gotta use it in, like, I don't know, don't go overboard with it, right? Don't just think that you're gonna throw 50 children out there and get super awesome performance. In general, you want to match your number of children in your cluster to either the number of physical cores or logical cores that you have. And when I say logical cores, remember that sometimes your CPU your operating system interprets one processor or one core as being like 2. In the case of like multi-threading stuff, in general, I use physical core count, but some of the documentation that you'll see around clustering uses logical cores instead. Using logical cores instead is okay because it does mean that you will handle concurrent requests a little bit better when they are low on CPU requirements. But when it starts to come down to really heavy processing requirement, in general, you kind of want to match up your number of CPUs to your number of children. Just my personal opinion. Okay, so that's been probably way more about clustering than you've ever wanted to know. However, we've still got a pretty basic example here. So let's come back in the next section and we're going to kind of supercharge our clustering setup with an open source project and give you something more production ready to run on your own projects. So quick break and I'll see you in a minute. In the last section, we had a very long discussion about clustering, and I think you now have a better idea of where we start to run into some diminishing returns as we increase the number of children inside of our cluster. Now, at present, our clustering setup inside of our index.js file is really straightforward and very simplistic. I definitely could show you how to build out a more fully featured clustering solution where our master tries to monitor the health of every child and maybe restart them if they ever crash or anything like that. But I'll be honest with you, that would be a little bit disingenuous on my part for one very good reason. There is already an open source project in the Node community for the best darn cluster management software that has ever been written. And in good faith, I really cannot tell you to try to write your own cluster management stuff for any reason beyond educational. So if you ever want to use cluster management in a production application, there's really one place you should turn, and that is to the PM2 CLI. So let's take a look at the documentation in this section. We're then going to install this CLI onto our local machines and then play around with it a little bit in the next video just to get a better idea of how it actually works. Okay, so I'm at the GitHub page for PM2. I'm going to paste the link here nice and large so you can very easily see it on the screen. There we go. So github.com/unitech/PM2. The GitHub page has some limited documentation for this module. If you go to pm2.io, which is the homepage, they've also got a huge collection of guides here as well on how to set this thing up for all different types, like really all different types of usages on this documentation page. So we're going to install this and just try it out very quickly on our personal project here. But I would really encourage you to take a look at some of the documentation here, because just about any question you probably have, they already have some documentation around it. Honestly, like I said, I could show you how to do some of this stuff yourself, but it's probably, honestly, I hate saying this, to be honest, it's probably just not the best use of time to try to rebuild the wheel from scratch here, because this really is a very solid piece of software. Okay, so let's install this very quickly, and then we will use it very briefly in the next section. So back in my terminal, I'm going to install PM2 by running npm install -g PM2, and that's going to install it as a global module. Now, when you run this command, if you get something complaining about permissions on your machine and you're running on Linux or OS X, you can try prepending this command with sudo, unless you don't feel like doing that, at which point I kind of leave it up to you to get this thing installed. A lot of people don't like it using sudo on any command whatsoever, so I kind of leave it up to you if you don't want to do that. Anyways, I'm going to let this install, and we'll come back in the next video and play around with it a little bit. In the last section, we installed the PM2 Process Manager on our local machine. This is a cluster management solution, so it has everything having to do with spawning multiple instances of your application and managing the health of every single one of them. So this PM2 module that we just installed is going to do really fancy things, like say if one of your instances ever crashes, it's going to automatically restart it for you. As I was gushing about it in the last video, it really is a pretty nice piece of software, very widely used in production deployments. So in this section, we're just going to get a little bit more familiar with how it works. Before we actually try it out, however, recall that inside of our index.js file right now, we still have a lot of stuff in here related to setting up clustering ourselves. So we don't really want to use PM2 on top of an existing cluster thing right here. So we're going to do a little bit of cleanup inside this file. If you want to back up the contents of this thing right here, feel free to make a duplicate of this file, because we are going to delete a lot of the clustering related stuff inside of here. So essentially, I'm going to go all the way down to the else statement right here, right about here or so, and I'm going to delete everything above it related to clustering. I'll then go down to the very bottom of the file where we had the closing curly brace for our else statement, and I'm going to delete that as well. And I'm going to dedent this thing, outdent I guess, and I'll save the file. So now we're back to the case where we're not doing anything with trying to set up clustering or anything like that. We're just going to delegate all that behavior over to PM2. Okay, so now we are back to normal here. I'm going to go back over to my terminal, and I'm going to make sure I'm still inside of my project directory. I'm also going to make sure that I don't have my server running right now. So I'm not running my server in any other window, because if I am, I will see an error message when I try to start up my server. Okay, so to start up our application using PM2 in cluster mode, we're going to write out PM2 start index.js, and then we're going to pass in -i right here with a number. So the reason we're doing -i right here, and we don't always have to do this, is just because we just had a huge discussion about the number of workers that we have inside of our cluster. The -i right here is not quite so much the number of instances. It's a little bit more about figuring out, it's about letting PM2 decide how many instances to create for you. So a very common option to use here is 0. 0 says, hey, you know what, PM2, I don't know what to do here. Just figure out what to do for me. In that case, if you put in 0 right here, PM2 is going to set up a number of instances equal to the number of logical CPU cores on your computer. Now, I realized in the last section, I mentioned logical cores very briefly without really going into that. The difference between physical cores and logical cores in your CPU comes down to that topic of multithreading or hyperthreading. So my computer is a dual core machine, has 2 physical cores, but each core can process 2 threads at the same time. So 2 threads at a time times 2 cores equals 4 logical cores. So logical cores is the number of physical times the number of threads that they can process at any given point in time. So to figure out how many logical cores, if you pass in i-i0 right here, it will start up a number equal to the number of actual logical cores on your machine. Now you'll see that I've already started up my cluster here and I completely forgot about it. So I'm going to kill that one. And I'm going to start it up again, this time with -i0. And so you're going to see that PM2 clearly thinks I have 4 logical cores on my machine, and so it started up 4 separate instances of my application. Now you'll notice that this dumps me back at like the command line right here, but there's a couple of different commands that we can use to inspect these running instances that we have and do things like, say, pull logs from them or other things that you might want to do in a normal application. So first off, you can get a very quick summary of the health of all your running instances by running PM2 list, and this will print out that very short summary, a little table that shows you kind of like what's going on with your current cluster. We can also do PM2 show, and then the name of one of our instances over here, or the name of one of our applications. So my application name is index, and chances are yours is as well. So if I do PM2 show index, I then get some much more detailed information about everything that's going on in that set of children. I can also do PM2 monit. So not monitor, just monit. And when I run that one, it gives me this really cool little dashboard where I can scroll through all the different processes over here. To scroll through this list right here, use your up and down arrow keys. And then to actually go over here and inspect any logs that are being emitted by these different processes, you can do the right arrow over and then scroll through those. But in our case, we don't have any logs right now. So in general, you can use this thing just in a production environment, and it's going to take care of managing the health of every single one of your instances. So if one of these children end up crashing, no problem, PM2 is going to automatically restart it for you. To exit this dashboard right here, by the way, you can press Control-C. And then the very last thing that you probably want to know how to do is how to stop those running servers. So to stop that group of running children, we can do PM2, delete index, like so. And when we run delete, you'll see that it removes all those running children, and we're back to running nothing at all. Now to be clear, usually we use PM2 in production environments. So you will log on to some remote server through SSH or whatever deployment process you have, and then you can interact with PM2 in that fashion. But PM2 has a lot of other ways to get access to your remote servers and interface them, all inside that documentation I showed you just a little bit ago. So usually you're not going to quite use PM2 so much in a development environment beyond just to kind of start it up and say, okay, yeah, it looks like my application works and it's not doing anything funny. All right, so that's pretty much clustering in a nutshell. So we've seen some good examples of clustering. We also saw where it starts to fall down and where we might want to get that sweet spot on the number of children that we have available. Let's take a quick pause right here. In the next video, we're going to come back and we're going to start looking at worker threads for delegating work inside of our application. So quick break, and I'll see you in just a minute. In the last couple of videos, we spoke about using Node in cluster mode to dramatically enhance the performance of concurrent heavy-duty lifting that our application might have to do. We're now going to talk very briefly about worker threads as well. We're only going to spend a very little bit on worker threads here, just to give you a very quick example of how you might use them. The reason we're only going to spend a moment, just remember, worker threads are definitely still in the experimental stage, and so I'm really just showing you this just so you have some knowledge and just in case you're curious about how they're used at all. But in general, I highly recommend if your application needs to do some heavy lifting to make use of cluster mode. One other thing that I want to mention here is that I personally would probably not be using both these approaches inside of a single application unless I knew that I really had some very good reason for it. The use of worker threads uses that same thread pool that is managed by Libuv for doing stuff like handling that hashing function. And so while using worker threads and getting direct access to that is definitely useful, at the end of the day, we're still being limited by the the amount of overall processing power of our CPU. So it's definitely nice to have around, but it's not like a amazing processing approach that's going to dramatically speed up your application more than what clustering mode can do. Okay, so with that in mind, let's take a look at a small little project that we're going to use to implement these threads inside of our application. I'm going to go over to npmjs.com and we're going to search for a very specific package. So we're going to look for Webworker-threads. So this is the package that we're going to use to set up some worker threads inside of our application. The documentation has a little bit of information about what's going on here, but if you scroll down to like the introduction area, I'll be honest with you, a lot of this is going to be the same stuff that I just spent a lot of time telling you about anyways. So if you want to, certainly feel free to take a look at this. Otherwise, let's install the module and then we'll set this up in the next couple of videos. So I'm going to first flip back over to my terminal, and inside my project directory, we're just going to use the same index.js file as before. So I'm going to install that module that we just looked at with npm install -- save webworker -threads, like so. So let's let this run, and we will start working on the implementation in the next video. In the last section, we installed the Webworker Threads library, and we're going to start wiring it up inside this video. As a quick reminder, just remember that this really is some very experimental stuff that I'm just showing you in case you are curious for whatever reason. But in general, my personal opinion is to make use of cluster mode, and in particular the PM2 module, if you're concerned about getting some level of better concurrency inside of your Node application. Let's first get started by taking a quick look at a diagram that's going to explain how this Worker Threads library works, and then we'll actually implement it inside of our Express application. Okay, so this is the general idea of what's going on. At the top of this diagram, we have the thread that our application is running in. So essentially, this represents the event loop right here. And then on the bottom is the thread that will be created by this new worker object that is created by the Webworker Threads library. So this is a separate thread that is also running on our computer. Because it's in a separate thread, that means it can do a lot of blocking work or a lot of heavy calculations and not necessarily block any of the code that is being executed inside of our event loop. Before we actually make use of this library, one quick thing that I want to remind you of right now. Remember that a lot of code inside of the nodejs library, as we've already seen, already makes use of the Libuv Threadpool. So if you're thinking that we're going to be running like that hash function really quickly by making use of this thread right here, well, that's not entirely true, because our pbkdf2 function already runs inside of a separate thread to make sure that it does not block our event loop. So my personal opinion here is that this web worker stuff, not quite as useful, I would say. You know, I don't want to be like 100% saying don't use this, but just keep that in mind that sometimes you are already using code that is being executed in a separate thread anyways. So really you only want to use this thing if you have some really heavy duty business logic of your own that you want to execute off of the event loop thread. Now to communicate with this separate thread over here, we don't get to have like very direct means of conversation per se with the work that's being done in this worker. So in other words, we cannot freely reference variables inside of the worker from our application. We have to do some very direct means of conversation by using this post message and on message system. This worker interface box right here represents the worker object that you and I are going to create inside of our server. The worker interface then creates this worker thread, and we communicate back and forth between the two by using post message and on message. On message is a property that we are going to assign a function to. That function will then be invoked anytime we call post message on the opposing side. In other words, if you and I call post message from our server, it's going to invoke the function assigned to on message inside the worker. And then the opposite is true as well. So if we call post message over here, it'll invoke a function assigned to the on message property inside of our worker interface back over inside of our application. Now this definitely is turning into a little bit of a tongue tie kind of deal here. So let's actually write out some code and get a better idea of how this thing is put together. All right. Now I'm going to again just reuse our index.js file here. So if you want to back up any of the code inside of here, feel free to make a copy of the contents or whatever you wish to do. At the top, I'm going to first get started by requiring in that Webworker Threads library. So I'll say const worker equals require Webworker Threads, and then we want one specific property off this library called .worker, like so. Then down inside of my Git route handler, I'm going to remove the pbkdf2 function. So like I said just a moment ago, this pbkdf2 function is already using our existing thread pool. So if we used this thing to somehow run our or run that inside of this worker we're going to create kind of defeats the purpose, because it's already being created in a separate thread anyways. So we're going to again have to come up with some different type of worker function to simulate doing some work inside of our app. So I'm going to delete that thing, and in its place I'm going to create a new worker object. So this is going to be like this worker interface right here. So I'm going to say const worker equals new worker, and I'm going to pass a function into this thing. Now, one thing that's very important here, when we pass in this function, we cannot freely make access to variables declared outside of it. So if we have something out here like const a equals 1, when we declare this function right here, I cannot do a like console log of a and then expect if I update the value of a or something like that to see it reflected inside the function. The function that we put inside of here is essentially going to get stringified and thrown out to a totally separate area of our computer. And so we don't get to freely, easily access variables in the closure scope between these two. So just keep that in mind. That's why we're using that entire post message and on message setup anyways. Okay, so this gives us our worker. We're going to add some logic inside this function in just a minute. But first, let's make use of the post message and on message properties on the worker interface that we just created. So on this worker interface right here, we're going to define the onMessage property and assign it a function. So I'm going to say worker.onMessage equals function, like so. Now whenever our worker sends a message back to our application, this function right here will be called. One thing I want to point out to you is that I did not make a typo here with the lowercase m. This is on lowercase m message, like so. Then underneath this, we can send a message into this worker. So we can like push some data over into that running thread by calling worker.postMessage, like so. So we've now created the interface. We've said what should happen inside of our application whenever that thread posts a message back to us. And we have also called post message inside of our application. So this function call right here is represented by this box right here. And this onMessage property being assigned a function right here represents this box right here. So we've defined our application side interface for this worker thread. Now we're going to move into the worker itself and define the post message and on message functions over there. So we're now going to define what our worker should do when it gets sent some amount of data. So now inside of the worker right here, I'm going to first define this dot on message. And I'm going to assign that a function as well. Now, one thing I want you to take very special note of right now is that I'm using keyword functions all over the place right now, and I'm not using arrow functions. I'm using keyword function because notice how I'm referencing this dot on message. This inside of this function right here is equal to the thread itself, like not necessarily the operating system thread, but an object that represents the thread. If I used an arrow function right here, then inside of the function, this would refer to the context of our route handler, which is definitely not what we want. So I am using the function keyword very much on purpose right now. After defining that onMessage property, I'm then going to call post, I want to call this one inside the onMessage, post message, like so. So we've now put together the communication interface for the worker itself. So this onMessage equals function right here is represented by this box right here. It's the function we run when our application calls post message. And then inside of that function, you and I are calling post message right here. That represents this box right here. So when we call post message right there, it communicates something from our worker thread back up to our application. I know all this like duplicate post message on message stuff gets confusing, and that's just why I'm taking a little bit of time to make sure it's very clearly described. So now inside the body of this function, like right here, this area right here, this is what will be invoked when our application calls post message. So this is our opportunity right here to do some amount of work over inside that other thread, so some computationally expensive operation. Let that thread execute it, and then after that work is done, we can communicate the result back over to our application by calling post message. So let's kind of simulate doing a little bit of work inside of here. We're going to do a very simple little work function here. We're going to, rather than doing like that previous while loop where we wait for some time to pass, we're instead going to make a counter function that counts up to a very high number. And then we're going to return the result of that back over to our running application through post message. So I'm going to say let counter equal 0. And then we'll define a while loop that's going to run as long as counter is less than 1 times 10 to the 9th. So 1e9 right here is equivalent to like 10 followed by 9 nines, like so. That's what the 1e9 represents. And then while that's true, we're going to increment our counter by 1. Again, this is meant to just simulate some amount of work being done inside of our worker thread that eventually leaves us with some actual value that we might want to communicate back over to our side of the application. So after running all this work and ending up with this super high value for counter, we're going to communicate that result back over to our side of the application through post message. So I'm going to pass it into counter like so. When we call post message with counter right here, we're essentially saying take the counter that just got calculated inside of our worker, pass in a post message, and that gets communicated back over to our application, specifically into the on message callback. So that's this callback right here. So I think for right now, let's just put down about like my counter, and we'll console log the result and just see what happens. So let's take a quick pause right now. We'll come back in the next video and we'll test out this code and see how we're doing. In the last section, we started putting together our separate worker thread. At this point, our separate worker is doing some very simplistic work. Whenever our application calls post message, which occurs right here, our thread executes the function that gets assigned to on message. So that's this function right here. Our worker then declares a counter variable and counts from 0 all the way up to 10 times 10 to the 9th, whatever it was. It counts up to a very high number. And then it eventually communicates the result back over to our side of the application. So when our thread calls post message, the on message property back inside of our application gets invoked. So that should be my counter right here. And at present, we're just console logging out that value. So let's try running our server now, and we're going to test this out inside the browser and just see what happens. One thing I want to mention very quickly, notice that at present, we're just console logging this value, and we're not actually responding to the incoming request or anything like that. So we will see this hang inside the browser. All we're looking for right now is a logging statement out at the terminal. So I'm going to flip back over to my terminal. I'll start my server up with nodejs.js. And then I'll go back over to my browser. I'll open up a new browser tab. And I'm going to go to localhost 3000. Okay, so again, this page is not going to resolve to anything. If I go back over to my terminal, however, you'll see the console log appear right here. So it's data times 10 to like the 9th. That doesn't look like 9s, but maybe I'm off with like times 10 to the 9th. Whatever. You get the idea. There's a whole bunch of zeros here. I apologize for being off on that. I know I'm totally wrong, and someone's going to let me really know scientific notation here in the comments. I know it's going to happen, but it's okay. I welcome it. Anyways, so we can now see that clearly our worker thread is doing some big calculation here and then returning the result back over to our application. But we were just a little bit off here with the argument naming. So the object that came back right here was not the actual counter itself. It was some data object. So let's call that thing like, I don't know, message. And then we'll just console log out message.data instead. And then how about to respond to our actual request, whenever we get some message back over from that thread, we'll call res.send and we'll send back that number that just got calculated, like so. So let's now restart our server and try this out again. So I'm going to restart my server. I'll then refresh the page, and then this time I should fairly quickly see a result appear on the screen. unless I got an error. Let's double check. Oh, my mistake. Res.send, we passed in a number right there, and whenever Express sees a number, it assumes that we're trying to send a status code, not the number that we think we're sending. So to turn this thing into a number, we can just join it with a string, like so. So now that's going to be cast as a string, and Express should think, oh, we're not sending back a status code, we're sending back some just plain number. So I'll restart my server, and we'll try this one more time. Okay, there we go. So now we see that result computed by our separate thread up here on the screen. All right, that's kind of all I really want to do around worker threads at this point, just to show you, hey, this is a thing and this is how you communicate with them. If you read the documentation around Webworker Threads, the author here claims that there are some distinct performance benefits over using clusters, but honestly, I'm not in entire agreement with that. So my opinion really is make use of a cluster before you start reaching for these thread things. Now, last thing I want to run for you very quickly, just to show that we do get some level of concurrency out of this, is to do an actual benchmark as well. So with the benchmark, we can at least confirm that there is some real concurrency going on here, and we're not just like stacking up one request after another when we do this calculation. So if I do something like ab-c1 1 with localhost 3000. So this is going to do the count just exactly one time. We can time this, and then we can run it again with 2 requests running at the same time, and we should see more or less the exact same time. Remember, I'm on a dual core computer right now, so every operation that I do in like 2x2 concurrency is going to, in general, run like twice as quickly. Okay, so we'll run this one. It takes about 733 milliseconds. And so now if I do it with some level of concurrency here, so 2 at the same time, those worker threads should take advantage of the 2 cores that I have in my computer and run the same operation in roughly the same amount of time. Okay, and so I see about 791, which is close enough for me to feel like, yeah, that's pretty darn close. 796, wow, that's getting, okay, there we go. More or less, I'm pretty confident to say, yeah, it's basically going about the same speed. Okay, so that's pretty much it for worker threads. Let's continue in the next section, and we're going to start taking a look at our next big topic. So quick break, and I'll see you in just a minute.